When we gaze up at the night sky, we are confronted with a profound contradiction. The universe appears both incredibly full and impossibly empty. Countless stars twinkle against the darkness, galaxies spiral in distant corners, and planets orbit faithfully around their suns. Yet between these objects lies an expanse so vast and so empty that it challenges our very understanding of reality. Look up on a clear night, far from city lights. What do you see? Points of light scattered across a black canvas. But this simple observation raises a puzzling question. Why is there so much nothing? Why does emptiness seem to be the default state of our universe, with matter and energy appearing as rare exceptions to this rule? The human perspective is limited. Standing on our small world, we perceive the vastness of space through the narrow lens of our experience. We evolved on a planet teeming with life, where empty spaces are quickly filled. Our intuition tells us that emptiness is unnatural, that nature abhors a vacuum. Yet the cosmos defies this intuition at every scale. Consider the numbers. The nearest star to our sun, Proxima Centauri, sits a staggering 4.2 light-years away. That's over 40 trillion kilometers of nearly empty space. If our sun were the size of a grain of sand, Proxima Centauri would be another grain of sand 4.5 kilometers away. Between them, almost nothing. This emptiness becomes even more extreme when we look beyond our local stellar neighborhood. Our Milky Way galaxy contains hundreds of billions of stars, yet they are separated by such immense distances that if you were to randomly place yourself somewhere in the galaxy, the chances of being near any star would be vanishingly small. You would almost certainly find yourself in the void between stars, surrounded by darkness. And beyond our galaxy, the picture becomes even more stark. The Andromeda Galaxy, our nearest large galactic neighbor, lies 2.5 million light-years from us. If we were to shrink the Milky Way down to the size of a dinner plate, Andromeda would be another plate 25 meters away. The space between galaxies is not merely empty, it is a vacuum far more perfect than anything we can create in laboratories on Earth. This pattern of islands of matter in vast oceans of emptiness continues at every scale we observe. Galaxies cluster together in groups and superclusters, leaving behind enormous cosmic voids that can span hundreds of millions of light-years. These voids contain almost nothing at all, not stars, not galaxies, not even much of the mysterious dark matter that pervades the universe. Yet paradoxically, when physicists examine the nature of empty space, they discover it isn't truly empty at all. What we perceive as nothingness is actually a seething quantum foam, where virtual particles pop in and out of existence in timeframes too short for us to detect. Empty space contains dark energy, a mysterious force that makes up nearly 70% of the universe's energy content. Even the vast gulfs between galaxies contain trace amounts of hydrogen, about 1 atom per cubic meter on average. So what do we mean when we say space is empty? We mean that matter as we understand it, the atoms and molecules that make up stars, planets, and living things, is concentrated in relatively small pockets, leaving the overwhelming majority of the universe's volume largely devoid of substantial matter. This peculiar arrangement demands explanation. Why should matter clump together in specific places while leaving most of space barren? Why don't we see matter more evenly distributed throughout the cosmos? The answers lie in fundamental physics and the universe's earliest moments. The emptiness of space is not an accident, but a consequence of physical laws. Gravity pulls matter together, forming stars and galaxies, while the expansion of space itself pushes these structures apart. The balance between these opposing forces has shaped the universe's evolution over its 13.8 billion year history. Our human brains struggle to comprehend the true scale of cosmic emptiness. We're accustomed to a world where objects are relatively close together. Even our language betrays this limitation. We speak of things being astronomically distant or vanishingly small because we lack more precise ways to describe the extremes of cosmic scale. Consider this: if the entire solar system, from the Sun to the orbit of Neptune, were reduced to the size of a coffee cup, the nearest star would still be over 1,000 kilometers away. In between, a void so complete that it makes the most barren desert on Earth seem crowded by comparison. This emptiness extends beyond mere physical space. The universe is also mostly empty in terms of time. The cosmos has existed for nearly 14 billion years, yet technological civilization has been around for only a few thousand. If the universe's history were compressed into a single Earth year, humans would appear only in the final minutes of December the 31st. The rest of cosmic history would be largely devoid of conscious observers. Another kind of emptiness, perhaps even more profound than physical space. The contrast between cosmic emptiness and the richness of life on Earth creates a cognitive dissonance. We live on a planet where life has filled nearly every niche, from the deepest ocean trenches to the highest mountain peaks. Earth teems with billions of organisms, a planet so full of life that we've barely catalogued all its species. Yet this abundance exists as a tiny island in an ocean of cosmic emptiness so vast that it defies comprehension. Some philosophers and scientists have pondered whether this emptiness holds meaning. Is the universe's vastness a clue to our cosmic significance or insignificance? Are we important because we're rare or unimportant because we occupy such a tiny fraction of space? The emptiness of space forces us to confront our place in the cosmos in ways that can be deeply unsettling. Ancient cultures grappled with these questions in their own ways. Many mythologies depict creation as a process of filling a primordial void. In Norse mythology, the universe began as Ginnungagap, a great emptiness between regions of fire and ice. In Chinese cosmology, the universe emerged from Wuji, the boundless void. These myths suggest that humans have long recognized emptiness as the canvas upon which reality is painted. The ancient Greeks had their own concept of cosmic emptiness. Aristotle famously declared that nature abhors a vacuum, suggesting that true emptiness was impossible. Yet other Greek philosophers, particularly the atomists like Democritus, argued that atoms moved through empty space, a view surprisingly close to our modern understanding. This debate about the nature of emptiness spans the entire history of human thought. In indigenous Australian astronomy, the dark spaces between stars were as significant as the stars themselves. These dark constellations represented important figures in creation stories. Rather than seeing emptiness as nothing, these traditions recognized that emptiness itself has form and meaning, an insight that resonates with modern astrophysics, where the distribution of cosmic voids tells us much about the universe's structure. Buddhist philosophy has long emphasized the concept of shunyata, often translated as emptiness or voidness. This isn't mere nothingness, but rather the idea that all phenomena lack inherent, independent existence. In a striking parallel, modern physics reveals that what appears to be solid matter is mostly empty space, and that particles themselves are better understood as excitations in quantum fields rather than discrete objects. Modern astronomy has only deepened these ancient intuitions. As our instruments have grown more powerful, we've discovered that the universe is not only emptier than we imagined, but emptier than we could have imagined. The Hubble ultra-deep field image, taken over several days of observation, revealed thousands of galaxies in a patch of sky that appeared completely empty to the naked eye. Yet even this image, crowded with galaxies, represents a universe that is overwhelmingly vacant. The average density of matter in the observable universe is estimated to be about 6 hydrogen atoms per cubic meter. A vacuum so perfect that it would be considered impossible to achieve in any laboratory on Earth. If you removed all the empty space from the atoms that make up every human on the planet, the entire human race would fit into the volume of a sugar cube. Matter itself is mostly emptiness. This raises profound questions about the nature of reality. Is what we perceive as solid matter an illusion? Are the boundaries we draw between objects arbitrary, given that both objects and the space between them are mostly empty? Quantum physics suggests that the distinction between something and nothing is far blurrier than our everyday experience indicates. The emptiness of space also impacts how we think about our search for extraterrestrial life. The vast distances between stars mean that even if the galaxy is teeming with civilizations, they would be separated by gulfs so enormous that communication might be practically impossible. Radio signals from Earth have reached only a tiny bubble of our galaxy, about 100 light-years in radius, a minuscule fraction of the Milky Way's 100,000 light-year diameter. These vast distances have practical implications for our dreams of interstellar travel, even at the fastest speeds humans have achieved. The Voyager spacecraft travel at approximately 17 kilometers per second. It would take tens of thousands of years to reach even the nearest star systems. The emptiness of space creates a natural isolation that may explain why we haven't yet detected signs of extraterrestrial civilizations, despite the likely abundance of habitable planets. When the Voyager 1 spacecraft turned its camera back toward Earth in 1994, from a distance of about 6 billion kilometers, our planet appeared as nothing more than a pale blue dot in the vastness of space. As astronomer Carl Sagan poetically noted, on that dot, everyone you ever heard of, every human being who ever lived out their lives. This perspective emphasizes how the emptiness of space contextualizes all human experience. The vastness of space also affects how we conceptualize our future. If humanity ever hopes to explore beyond our solar system, we must contend with distances so great that they render traditional travel nearly impossible. Even at the speed of light, the cosmic speed limit according to Einstein's theories, it would take decades or centuries to reach the nearest stars and millions of years to cross the galaxy. Yet this emptiness has also protected us. The vast spaces between stars mean that catastrophic cosmic events, supernovas, gamma-ray bursts, even colliding galaxies, generally occur far enough away from Earth that their destructive effects are diminished. The emptiness of space may be a prerequisite for the long-term stability that allowed life to evolve on our planet. Consider the implications of a denser universe. If stars were much closer together, their gravitational influences would destabilize planetary orbits. Nearby supernovas would sterilize developing worlds with radiation. The night sky would blaze with the light of thousands of stars, making darkness a rarity and potentially altering the evolutionary path of life. Our very existence may depend on cosmic emptiness. When astronomers study the most distant regions of the observable universe, they're looking back in time due to the finite speed of light. The farther away an object is, the longer its light takes to reach us. This means we observe distant galaxies as they were billions of years ago. Remarkably, these ancient galaxies appear to be packed more closely together than those nearby, suggesting that the universe has become emptier over time as cosmic expansion has stretched space itself. This expansion creates a troubling prospect for the far future. As the universe continues to expand at an accelerating rate, galaxies will move beyond our cosmic horizon one by one. In 1 trillion years, future astronomers in our galaxy would see only darkness beyond the Milky Way's boundaries. The observable universe will appear emptier and emptier as time progresses. Eventually, even the stars in our own galaxy will burn out, leaving truly empty space in their wake. Theoretical physicists sometimes ponder whether the apparent emptiness of our universe might be an illusion of scale. String theory suggests that reality might have additional spatial dimensions beyond the 3 we perceive, but these dimensions are compactified, curled up so tightly that they're invisible to us. If true, what seems like emptiness might actually be incredibly dense with structure at scales far smaller than we can observe. There's another possibility too. What we perceive as emptiness might be full of dark matter and dark energy, mysterious substances that don't interact with light, and thus remain invisible to direct observation. Dark matter appears to form an invisible scaffolding throughout the cosmos, while dark energy permeates all of space uniformly. Together, they make up about 95% of the universe's total energy content. Perhaps the universe isn't empty at all. Perhaps we just can't see most of what's there. Some advanced theories even suggest that empty space contains enormous amounts of energy, the so-called zero-point energy, or vacuum energy. According to quantum field theory, even perfect vacuums experience tiny fluctuations in energy fields, creating and annihilating pairs of virtual particles continuously. If we could somehow tap into this energy, the emptiness of space would become the greatest energy resource imaginable. There's another perspective on cosmic emptiness that offers a more optimistic view. Perhaps the universe isn't empty at all. Perhaps it's exactly as full as it needs to be. The density of matter in the universe appears to be precisely calibrated. If the cosmos contained significantly more matter, gravity might have caused it to collapse back on itself long ago. If it contained much less, stars and galaxies might never have formed. The apparent emptiness may be a necessary condition for our existence. This idea connects to the anthropic principle, the notion that our observations of the universe are necessarily biased by the fact that we exist to make those observations. We can only observe a universe compatible with our existence, which might explain why we find ourselves in a cosmos that appears fine-tuned for life, despite its overwhelming emptiness. The emptiness of space also creates the conditions necessary for structure and complexity. In a uniformly filled universe, there would be no gradients, no dynamics, no flow of energy from high-density regions to low-density ones. The contrast between the emptiness of space and the density of matter creates the conditions for stars to shine, for planets to form, and ultimately for life to emerge. Our best models suggest that in the very early universe, quantum fluctuations in an otherwise perfectly uniform field created tiny variations in density. As the universe expanded, gravity amplified these variations, causing slightly denser regions to become even denser while emptying the spaces between them. What began as a nearly homogeneous cosmos gradually developed into the clustered, hierarchical structure we see today, with galaxies arranged in delicate filaments surrounding vast cosmic voids. These cosmic voids are not merely empty space, they're sculpted by the surrounding matter. Their size, shape, and distribution provide crucial information about the universe's composition and evolution. By mapping these voids, cosmologists can test theories about dark energy, dark matter, and the laws of gravity on cosmic scales. The emptiness itself becomes a tool for understanding the universe's fundamental nature. The concept of cosmic emptiness took center stage in astronomy during the early 20th century, when Edwin Hubble demonstrated that many nebulae were actually distant galaxies, island universes far beyond our own Milky Way. This discovery vastly expanded the scale of the known universe and revealed the immense gulfs of empty space between galaxies. Hubble's later discovery that these galaxies are moving away from each other confirmed that space itself is expanding, making the universe effectively emptier with each passing moment. When we peer through our most powerful telescopes at the most distant observable regions of the universe, we're looking back in time to just a few 100 million years after the Big Bang. Even then, the universe appears structured, with proto-galaxies already forming. The seeds of today's cosmic emptiness were present almost from the beginning, a testament to how fundamental this arrangement is to the universe's nature. Physicists have even suggested that the apparent emptiness of our universe might be evidence for the multiverse hypothesis. Perhaps our universe is just one of many, each with different physical constants and distributions of matter. In this vast ensemble of universes, most might be too dense or too empty to support complexity. We necessarily find ourselves in one of the rare universes with just the right amount of emptiness. Some versions of inflationary theory, our best model for the universe's earliest moments, suggest that the process that created our universe continues eternally, spawning countless other universes in an ever-expanding multiverse. If true, our universe with its particular balance of matter and emptiness is just one possibility among an infinite array of cosmic configurations. The concept of emptiness takes on different meanings in different branches of physics. In quantum field theory, the vacuum isn't empty, but full of fields in their lowest energy states. In general relativity, empty space has a geometry that can be warped by mass and energy. In string theory, apparent emptiness might conceal dimensions beyond our perception. As physics advances, our understanding of cosmic emptiness continues to evolve. As we peer deeper into space using ever more powerful telescopes, we continue to refine our understanding of cosmic emptiness. The James Webb Space Telescope, Hubble's successor, will allow us to see farther into the universe than ever before, potentially revealing new insights about the distribution of matter in the cosmos and the nature of the void that surrounds it. Future observatories may map the distribution of dark matter with unprecedented precision, revealing invisible structures that permeate what appears to be empty space. Advanced gravitational wave detectors will sense ripples in space-time caused by violent cosmic events, providing a new way to see through the apparent emptiness. Each technological advance pushes us closer to understanding why our universe has the structure it does. Artists and writers have often grappled with the emotional and philosophical implications of cosmic emptiness. The vastness of space has inspired awe, terror, wonder, and despair, sometimes all at once. From Pascal's meditation on the eternal silence of these infinite spaces, to Carl Sagan's more optimistic take on our place in the cosmos, human culture reflects our ongoing struggle to reconcile the emptiness above with the richness of life around us. For many, the emptiness of space evokes existential questions. In a universe so vast and so empty, what meaning can human existence have? Yet others find inspiration in this very emptiness. The rarity of complex structures like galaxies, stars, planets, and especially life in the cosmic void makes them all the more precious. Perhaps value comes not from abundance but from contrast. Islands of complexity and consciousness in an ocean of simplicity. The practical implications of cosmic emptiness extend to our future as a species. If humanity is to survive the eventual death of our sun, we must one day venture into the void between stars. The emptiness of space presents both our greatest challenge and our only long-term hope. Overcoming the vast distances between habitable worlds will require technological innovation beyond anything we can currently imagine. To truly understand why the universe is so empty, we need to journey back to its very beginning. We need to examine how space itself came to be, how the first particles formed, and how the structures we see today emerged from the primordial chaos of the early cosmos. The story begins with the most energetic event we can conceive, the Big Bang. Not an explosion in space, but an explosion of space. A moment when everything we know, including space and time themselves, burst into existence from a state of unimaginable density and temperature. In those first moments, there was no emptiness. The universe was filled completely with energy so intense that matter, as we know it, couldn't exist. But as space expanded and temperatures dropped, particles began to form, setting in motion the cosmic processes that would eventually create the sparse, structured universe we observe today. The emptiness of space raises questions about life beyond Earth. If habitable planets are as rare as they appear to be, separated by gulfs of empty space measured in light years, then intelligent civilizations might be effectively isolated from one another. Interstellar communication would be limited by the speed of light, making conversations across the void a generational endeavor. Any messages we send today might not receive responses for decades or centuries. This isolation might explain one aspect of the Fermi Paradox, the apparent contradiction between the high probability of extraterrestrial civilizations and our lack of contact with them. Perhaps the universe teems with intelligent life, but the emptiness between stars serves as a natural quarantine, preventing interstellar civilizations from emerging. The void between stars might be an impassable moat around each inhabited world. When astronauts describe the experience of seeing Earth from space, they often mention a cognitive shift called the overview effect, a profound realization of Earth's fragility as a tiny oasis in a vast cosmic desert. This perspective often inspires a deep sense of unity with all humanity and a desire to protect our planet. The emptiness of space, paradoxically, helps us appreciate the fullness of life on Earth. The emptiness of space is not a bug in the universe's design, but a feature, a necessary condition for the formation of stars, planets, and ultimately, life itself. Had matter been distributed perfectly evenly throughout the cosmos, gravity would never have been able to form the dense regions where stars could ignite. Without the contrast between emptiness and density, without the vast voids between islands of matter, the conditions for our existence might never have arisen. As we continue our exploration, we'll travel back to the universe's infancy, when today's emptiness was just beginning to take shape. We'll examine how the cosmos transformed from a uniform sea of energy into the complex tapestry of galaxies, stars, and planets we see today. And we'll confront the profound implications of living in a universe that is, by any measure, overwhelmingly empty. This journey will challenge our intuitions and expand our perspective. It will force us to reckon with scales and time periods far beyond human experience. But it will also reveal the deep connections between the largest structures in the universe and the particles that make up our own bodies. The emptiness of space is not something separate from us. It is the canvas upon which the story of the cosmos and our own story is written. By understanding this emptiness, we come closer to understanding our place in the universe and the extraordinary set of circumstances that allowed us to exist at all. So join us as we explore the paradox of cosmic emptiness, a journey that will take us from the first moments after the Big Bang to the far future of our expanding universe, from the largest structures in the cosmos to the quantum realm. Together, we'll unravel the mystery of why the universe appears so vast and so empty, and what this emptiness tells us about the nature of reality itself. To understand the emptiness of today's universe, we must journey back to a time when emptiness didn't exist at all, the birth of the cosmos itself. 13.8 billion years ago, something extraordinary happened. The universe as we know it burst into existence in an event we call the Big Bang. But the Big Bang wasn't an explosion in space. It was an explosion of space, the sudden birth of both time and space from a state that defies our conventional understanding. In the beginning, there was no emptiness to speak of. The entire observable universe was compressed into a volume smaller than the period at the end of this sentence. A state of energy so concentrated that the laws of physics, as we understand them, break down completely. This initial state had a temperature of over 1,000,000 trillion degrees, so hot that no particles could exist. Instead, the infant universe was filled with a dense, uniform soup of pure energy. This primordial state was as far from emptiness as we can imagine, a cosmos filled completely with raw, undifferentiated potential. As this initial plasma began to expand and cool, the first elementary particles began to form. Within the first microsecond after the Big Bang, quarks and electrons emerged from the cooling energy field. Space itself was expanding at an extraordinary rate, but it remained filled with particles so densely packed that they were in constant collision, forming a plasma so thick that even light could not travel freely. For the first 380,000 years of cosmic history, the universe was effectively opaque. Photons, particles of light, couldn't travel far before being absorbed or scattered by the dense particle soup. This period is often called the Cosmic Dark Ages, though ironically, the universe was actually filled with intensely hot, bright radiation that simply couldn't escape the cosmic fog. During these early moments, the universe was expanding rapidly, but it wasn't becoming empty in the way we might intuitively understand. Rather than particles moving away from each other through existing space, space itself was stretching, carrying particles along with it. The density of the universe was decreasing, but it remained extraordinarily full by today's standards. The seeds of today's cosmic emptiness were planted during an even earlier phase of the universe's history, a period called cosmic inflation. According to this theory, in the first fraction of a second after the Big Bang, the universe underwent a period of exponential expansion, doubling in size every billion trillion trillionth of a second. This inflationary period, which lasted just 10 to the negative 35 seconds, expanded the universe by the factor of at least 10 to the 26. To put this in perspective, that's like going from the size of a proton to the size of a grapefruit in less time than it takes light to cross a single proton. This extraordinary stretching of space laid the groundwork for the vast emptiness we observe today. During inflation, tiny quantum fluctuations in the fabric of space-time were stretched to cosmic scales. These fluctuations created slight variations in the density of the universe, areas that were infinitesimally more dense than others. These minute differences would eventually become amplified by gravity, leading to the formation of galaxies and consequently the vast voids between them. But why did inflation occur? The leading theory suggests that in its earliest moments, the universe was dominated by a peculiar state called a false vacuum, a high-energy configuration that was momentarily stable but destined to decay. As this false vacuum decayed into a lower energy state, it released enormous energy, driving the exponential expansion of space. The concept of inflation explains several puzzling features of our universe. It explains why the cosmos appears remarkably uniform on large scales, why space seems flat rather than curved, and why we don't observe magnetic monopoles, exotic particles predicted by many theories but never detected. Most importantly for our story, inflation helps explain why the universe is so vast and by extension so empty. When inflation ended, the enormous energy that had driven the exponential expansion was converted into particles and radiation in a process called reheating. This marked the beginning of the hot Big Bang as we traditionally understand it, the dense, high-temperature state from which our observable universe evolved. After inflation, the universe continued to expand, though at a much slower rate. For the first few minutes, the temperature and density remained high enough for nuclear fusion to occur throughout space. During this brief window, protons and neutrons combined to form the nuclei of the lightest elements, primarily hydrogen and helium, with traces of lithium. This process, called Big Bang nucleosynthesis, created the raw materials from which the first stars would eventually form. But it's important to note that even at this stage, the universe was still incredibly dense by modern standards. There were no stars, no galaxies, and certainly no vast empty voids. Instead, the cosmos was filled with a nearly uniform mixture of radiation and the nuclei of light elements. As the universe continued to expand and cool, it reached a critical threshold at around 380,000 years after the Big Bang. The temperature fell to roughly 3,000 degrees Kelvin, cool enough for electrons to combine with nuclei, forming the first neutral atoms. This moment, called recombination, marked a profound transformation in the character of the cosmos. With electrons now bound to nuclei rather than free to interact with photons, light could suddenly travel freely across space. The universe became transparent. The radiation that was released at this moment has been traveling through space ever since, gradually stretched by cosmic expansion until today it forms a faint microwave background that permeates the entire universe. This cosmic microwave background radiation, or CMB, was first detected in 1965 and provides our earliest possible view of the universe. It reveals a remarkably uniform cosmos. The temperature variations in the CMB are mere fractions of a degree. These tiny fluctuations, however, are the imprints of the quantum fluctuations that were stretched during inflation, the seeds that would eventually grow into today's cosmic structures. After recombination, the universe entered a period often called the Dark Ages, distinct from the earlier opaque phase. During this time, which lasted for hundreds of millions of years, the universe contained no sources of visible light. It was filled with neutral hydrogen and helium gas, extremely diffuse by big earthly standards, but far denser than the intergalactic medium today. This dark period ended with the formation of the first stars, roughly 100 to 200 million years after the Big Bang. These pioneering stars were likely giants, perhaps 100 or more times more massive than our Sun, forming from the gradual collapse of primordial gas clouds under their own gravity. These first stars were composed almost entirely of hydrogen and helium, unlike modern stars which contain heavier elements created in previous generations of stars. Their immense size and purity made them extraordinarily hot and bright, and their intense ultraviolet radiation began to reionize the neutral hydrogen that filled the universe. This period of reionization marked another fundamental change in the universe's character. The intense radiation from the first stars, and later the first quasars, supermassive black holes actively consuming matter, stripped electrons from hydrogen atoms throughout the cosmos. Once again, much of the matter in the universe became an ionized plasma, though far less dense than before recombination. By about 1 billion years after the Big Bang, the universe had become largely transparent to ultraviolet light, a state that persists to the present day. But even at this relatively late stage in cosmic history, the universe still contained far more matter per unit volume than it does today. The process of cosmic emptying was well underway, but far from complete. As the first stars began to form, they didn't distribute themselves evenly throughout space. Instead, they clustered in regions where the primordial gas was slightly denser. Those same regions that originated as quantum fluctuations during inflation were stretched to cosmic scales and then were amplified by gravity over hundreds of millions of years. This clustering happened because gravity is a runaway process. Regions with slightly more matter exert slightly stronger gravitational pulls, drawing in more matter, which increases their gravitational influence further. Over time, this positive feedback loop causes matter to concentrate in certain regions while evacuating others, creating the contrast between cosmic structures and voids. The first galaxies began to form around this same time, roughly a few 100 million to 1 billion years after the Big Bang. These primordial galaxies were smaller and more chaotic than the majestic spiral and elliptical galaxies we see today. They formed as gravitationally bound collections of those first-generation stars, often colliding and merging with one another as they evolved. These early galaxies were also much closer together than galaxies are today. The continued expansion of space has stretched the distances between galaxies over billions of years, contributing significantly to the emptiness we observe in the modern universe. When we look at ancient galaxies through powerful telescopes, we're seeing them as they were billions of years ago, and they appear more tightly packed than their modern counterparts. This observation leads to a profound realization. The universe has become progressively emptier throughout its history. This emptying is driven by two main factors: the continued expansion of space and the clustering of matter due to gravity. As space expands, the average density of matter decreases, and as gravity pulls matter into stars, galaxies, and larger structures, the contrast between these structures and the voids between them increases. The role of dark matter in this process cannot be overstated. Dark matter is an invisible form of matter that doesn't interact with light, but does exert gravitational influence. Observations of galaxy motions and other cosmic phenomena suggest that dark matter outweighs ordinary matter by a factor of roughly 5 to 1. Dark matter appears to have played a crucial role in shaping the universe's structure. Since it doesn't interact with radiation, dark matter began to clump together under its own gravity earlier than ordinary matter, which was kept relatively smooth by its interactions with the intense radiation of the early universe. These initial dark matter clumps formed gravitational wells that ordinary matter later fell into, accelerating the formation of galaxies. This process created a cosmic web structure that we observe today, a network of dark matter filaments with galaxies strung along them like pearls, surrounding vast cosmic voids. These voids are the emptiest regions of the modern universe, containing so little matter that they've been called the deserts of the cosmos. Around 2 billion years after the Big Bang, another factor began to influence the evolution of cosmic emptiness: dark energy. Observations of distant supernovae in the late 1990s revealed that the expansion of the universe is actually accelerating, contrary to what would be expected if gravity were the only force at play on cosmic scales. The leading explanation for this acceleration is a mysterious repulsive force called dark energy. which appears to permeate all of space uniformly. Unlike matter, both ordinary and dark, which becomes more diffuse as the universe expands, the energy density of dark energy remains constant as space stretches. This means that as the universe grows larger, dark energy comes to dominate over matter and radiation. The discovery of dark energy revolutionized our understanding of cosmic history and destiny. If current models are correct, the universe underwent an initial period of deceleration due to the gravitational attraction of matter, but around 5 billion years ago, the ever-diluting matter density fell below the constant density of dark energy. At this point, expansion began to accelerate again, and it has been accelerating ever since. This acceleration is literally stretching the universe apart, making it emptier at an increasing rate. In the far future, this process will isolate galaxies from one another, eventually making other galaxies unobservable from our vantage point as they recede beyond our cosmic horizon. But the influence of dark energy on cosmic emptiness isn't limited to the future. Even now, it's enhancing the contrast between cosmic structures and voids. While gravity continues to draw matter together within galaxies and galaxy clusters, dark energy prevents these clusters from merging on the largest scales, preserving and even enhancing the voids between them. The interplay between ordinary matter, and dark energy has shaped the universe's evolution from a nearly uniform soup of subatomic particles to the complex tapestry of structures and voids we observe today. This narrative helps explain why the universe appears so empty from our perspective. It has been becoming emptier throughout its entire history. Yet there's a paradox here. While the universe as a whole has been becoming less dense, the matter within it has been clumping together more tightly. Stars are much denser than the primordial gas from which they formed. Galaxies represent enormous concentrations of matter compared to the intergalactic medium. Even as cosmic expansion has been diluting the universe overall, gravitational attraction has been creating local pockets of extremely high density. This contrast between density and emptiness is essential for the emergence of complexity. In a perfectly uniform universe, there would be no stars, no planets, and no possibility for life as we know it. The emptiness between structures is the necessary counterpart to the complexity within them. Consider our own solar system as a microcosm of this principle. The space between planets might seem wastefully empty, but this emptiness provides the stability that allows planets to maintain their orbits over billions of years. If the planets were much closer together, their gravitational interactions would create chaos, potentially ejecting worlds from the system or causing catastrophic collisions. Similarly, on a galactic scale, the vast distances between stars allow for stable planetary systems to exist. If stars were much closer together, their gravitational tugs would disrupt planetary orbits, and their intense radiation would make many worlds uninhabitable. The emptiness of space, far from being a bug in the cosmic design, might be a feature necessary for the emergence of life. As we've seen, the universe was never truly full in the sense of being completely filled with solid matter, but it was once far denser and more uniform than it is today. The story of cosmic evolution is partly a story of increasing emptiness as space expands and matter clumps together under gravity's influence. Yet this increasing emptiness has been accompanied by increasing complexity. From a nearly uniform plasma emerged atoms, which clustered into clouds, which collapsed to form stars and planets. On at least one of those planets, atoms arranged themselves into molecules, which eventually gave rise to living organisms, which ultimately evolved the capacity to look up at the night sky and wonder about their place in the cosmos. Perhaps the most remarkable aspect of this story is that the vast emptiness of the universe, far from being a meaningless void, turns out to be precisely the condition needed for the emergence of structure, complexity, and eventually consciousness. The emptiness isn't a vacuum awaiting content, it's the canvas that allows cosmic art to exist at all. In this light, the question, why is the universe so empty, takes on a different character. Perhaps a better question is, could a universe less empty than ours support the complexity needed for life? The evidence suggests that the answer may be no. The emptiness of space, rather than being a puzzling feature requiring explanation, might instead be a necessary precondition for our existence. The early universe's journey from incredible density to relative emptiness was governed by fundamental physics, the interplay of quantum mechanics, general relativity, and the essential forces of nature. The emptiness we observe today isn't random or meaningless. It's the predictable outcome of physical laws operating over cosmic timescales. This realization connects our story back to the quantum fluctuations that occurred during inflation. Those tiny ripples in the fabric of space-time, stretched to cosmic scales by inflation and then amplified by gravity over billions of years, grew into the large-scale structure we observe today. Galaxies, galaxy clusters, filaments, and voids. The emptiness of the modern universe, then, is the echo of quantum processes that occurred in the first fraction of a second after the Big Bang. The same physics that governs particles in accelerators on Earth shaped the grandest structures in the cosmos. This connection across scales and across time reveals the deep unity underlying the apparent diversity of physical phenomena. As we transition to the next part of our journey, we'll explore how these early processes led to the formation of the galaxies we see today. We'll examine how these vast collections of stars organized themselves into the spectacular spiral and elliptical forms that populate the modern universe, and how the spaces between them became the cosmic voids that characterize our landscape on the largest scales. The story of increasing cosmic emptiness isn't over. It continues today and will stretch far into the future. But to understand where the universe is going, we need to understand how it evolved from its dense beginnings to create the structures we observe in the present day, islands of matter in an ocean of seemingly empty space. Our journey will take us from the largest scales of cosmic structure to the intimate scales of our local galactic neighborhood. We'll see how the universe's evolution from uniformity to emptiness created the conditions necessary for our existence, and how the interplay between matter, energy, and empty space continues to shape cosmic destiny. The emptiness of the universe isn't a vast nothingness awaiting explanation. It's an integral part of the cosmic narrative, as essential to the story as the stars themselves. Without the void, there could be no structure. Without the darkness, we could never see the light of distant galaxies. The emptiness, it turns out, is full of meaning. As we journey forward in cosmic time, roughly 1 billion years after the Big Bang, the universe was undergoing a profound transformation. The first stars had already lived and died, enriching the cosmos with heavy elements forged in their cores and explosive deaths. In their wake, a new era of cosmic evolution was beginning, the birth of the majestic structures we call galaxies. Galaxies, vast collections of stars, gas, dust, and dark matter, represent the fundamental building blocks of cosmic structure. Today, we observe hundreds of billions of galaxies in the observable universe, each containing billions or even trillions of stars. Yet these immense stellar cities occupy only a tiny fraction of the universe's volume. The rest is an immense void, a cosmic desert largely devoid of luminous matter. To understand why galaxies formed as isolated islands, rather than being evenly distributed throughout space, we need to examine the subtle interplay between gravity, cosmic expansion, and the fluctuations imprinted on the universe during its earliest moments. The story begins with those tiny quantum fluctuations that occurred during inflation, stretched to cosmic scales, and left their mark on the cosmic microwave background radiation. These fluctuations created regions that were slightly denser than average, perhaps only 1 part in 100,000 denser. This might seem insignificant, but given enough time, gravity can amplify even the slightest density contrast. Gravity, after all, is a cumulative force. A region that's slightly denser than its surroundings exerts a slightly stronger gravitational pull, drawing in more matter from its vicinity. This additional matter increases the region's density further, enhancing its gravitational attraction and accelerating the process of accumulation. What begins as a barely perceptible difference in density can, over hundreds of millions of years, grow into the spectacular structures we observe today. But this process didn't happen uniformly throughout space. The initial density fluctuations varied from place to place, creating a complex pattern of regions with slightly higher and slightly lower density than average. As gravity went to work, the denser regions grew denser, while the less dense regions became more depleted, increasing the contrast between them. Dark matter played a crucial role in this process. Since dark matter doesn't interact with radiation, it began to clump together under its own gravity earlier than ordinary matter, which was kept relatively smooth by its interactions with the intense radiation of the early universe. By the time the universe became transparent and ordinary matter was free to collapse gravitationally, dark matter had already formed a network of densely concentrated filaments and nodes. This dark matter scaffolding guided the collapse of ordinary matter. Drawn by the gravitational pull of dark matter concentrations, hydrogen and helium gas flowed into these regions, becoming dense enough to form stars. The first galaxies formed at the intersections of dark matter filaments, where the gravitational pull was strongest. The earliest galaxies were unlike those we see today. They were smaller, more irregular, and contained stars that were almost pure hydrogen and helium. These first-generation stars, lacking the heavy elements present in modern stars, had different properties. They were generally more massive and burned hotter and brighter than stars in our current epoch. As these early galaxies evolved, they experienced frequent collisions and mergers with other young galaxies. These violent encounters triggered intense bursts of star formation and helped build larger galactic structures. The most massive galaxies we observe today, giant ellipticals containing trillions of stars, grew primarily through this process of galactic cannibalism, consuming hundreds of smaller galaxies over billions of years. Meanwhile, the space between these nascent galaxies was becoming progressively emptier. As matter flowed into the developing galaxies, it left behind regions of lower than average density. The continuing expansion of the universe stretched these regions further, while the mutual gravitational attraction of galaxies organized them into clusters and superclusters, defining the voids between them more sharply. By about 2 billion years after the Big Bang, the basic structure of the cosmic web was in place. Galaxies and galaxy clusters had formed along dark matter filaments, creating a network that resembled a three-dimensional spider web or the neurons in a brain. Between these filaments lay vast cosmic voids, regions with significantly less matter than the cosmic average. These voids are among the most striking features of our universe's large-scale structure. The largest, such as the Boötes void, span hundreds of millions of light-years. Despite their name, these voids aren't completely empty. They contain a diffuse distribution of hydrogen gas and a few isolated galaxies. But compared to the dense regions of the cosmic web, they represent enormous volumes with very little matter. The contrast between the cosmic web and the voids between its filaments raises an important question. Why isn't matter distributed more uniformly throughout the universe? The answer lies in the fundamental instability of a uniform matter distribution under the influence of gravity. Even a perfectly uniform distribution of matter would, over time, develop structures due to the growth of tiny random fluctuations. In mathematical terms, a uniform distribution is unstable against gravitational collapse. Given enough time, even quantum fluctuations would grow into large-scale structures through the relentless pull of gravity. But our universe didn't start with a perfectly uniform distribution. The inflationary period in the universe's first fraction of a second stretched quantum fluctuations to cosmic scales, creating the seeds for all the structure we observe today. These seeds were tiny, density variations of just 1 part in 100,000, but they provided the initial conditions that gravity needed to create galaxies and voids. The pattern of these initial fluctuations wasn't random. Cosmologists believe they followed a specific statistical pattern called a nearly scale-invariant spectrum, which means that fluctuations occurred on all size scales with roughly equal strength. This pattern, predicted by the theory of cosmic inflation, has been confirmed by observations of the cosmic microwave background and the distribution of galaxies. This specific pattern of initial fluctuations helps explain the particular arrangement of galaxies and voids we observe. If the fluctuations had been stronger on large scales, we might see a universe with larger voids and more massive superclusters. If they had been stronger on small scales, we might see a more uniform distribution of smaller galaxies. The universe we observe reflects the actual pattern of fluctuations that existed in its earliest moments. As galaxies continue to evolve, they developed into the diverse forms we see today. Some became spiral galaxies like our Milky Way, with elegant arms spiraling outward from a central bulge. Others became elliptical galaxies, spheroidal or football-shaped collections of older stars with little ongoing star formation. Still others became irregular galaxies with no discernible structure, often due to disruptive gravitational interactions with neighboring galaxies. The form a galaxy takes is influenced by its history, particularly its history of mergers with other galaxies. Spiral galaxies generally form when galaxies evolve in relative isolation, allowing them to settle into orderly rotating disks. Elliptical galaxies typically result from the merger of two or more large galaxies, which disrupts their orderly motion and creates a more randomly organized stellar system. Our own Milky Way galaxy, a barred spiral containing about 400 billion stars, has evolved through both processes. It grew partly through the steady accretion of gas from the intergalactic medium, forming new stars and spiral arms, and partly through mergers with smaller galaxies. Even now, it's in the process of consuming several dwarf galaxies, including the Sagittarius dwarf spheroidal galaxy, whose stars are being stretched into a long stream as they're incorporated into our galaxy. The Milky Way isn't alone in space. It's part of the Local Group, a collection of over 50 galaxies dominated by our galaxy and the Andromeda Galaxy. The Local Group, in turn, is on the outskirts of the Virgo supercluster, a collection of galaxies spanning about 110 million light-years. Recent observations suggest that the Virgo supercluster is itself part of an even larger structure called Laniakea, a supercluster complex spanning about 520 million light-years and containing about 100,000 galaxies. Laniakea, whose name means immense heaven in Hawaiian, is one of millions of similar supercluster complexes in the observable universe. These vast cosmic structures, galaxies, galaxy clusters, superclusters, and supercluster complexes form a web-like pattern when viewed on the largest scales. This cosmic web is characterized by long, thin filaments of galaxies connecting dense nodes where multiple filaments meet. Between these filaments lie the vast cosmic voids, regions where galaxies are few and far between. This pattern, dense filaments surrounding vast voids, emerges naturally from the growth of structure under the influence of gravity. Computer simulations that start with tiny density fluctuations, consistent with those observed in the cosmic microwave background, and then apply the laws of gravity and cosmic expansion, produce structures remarkably similar to what we observe in the actual universe. These simulations reveal that the cosmic web we observe today is the inevitable result of the universe's expansion, the pull of gravity, and the particular pattern of initial density fluctuations. The emptiness between galaxies isn't a random feature, it's a necessary consequence of the physics that governs our universe. But what exactly is in these cosmic voids? While they contain far less matter than the filaments and nodes of the cosmic web, they aren't completely empty. They contain extremely diffuse hydrogen gas, with perhaps 1 atom per cubic meter, about 1 trillion times less dense than the best vacuum we can create on Earth. They also contain dark matter, though at densities well below the cosmic average. Perhaps most surprisingly, voids aren't entirely devoid of galaxies. They contain what astronomers call void galaxies, relatively isolated galaxies that formed in the underdense regions between filaments. These galaxies are typically smaller and have had different evolutionary histories than galaxies in denser environments. They've experienced fewer mergers and interactions with other galaxies, often resulting in pristine spiral structures. The existence of void galaxies highlights an important aspect of cosmic structure formation. It's a statistical process. While gravity tends to draw matter toward overdense regions, random motions and local fluctuations can occasionally lead to galaxy formation, even in underdense regions. The distribution of matter in the universe follows overall patterns, but allows for exceptions and variations. The relationship between galaxies and voids is reciprocal. While it's natural to think of galaxies forming first and voids as simply the spaces left between them, the reality is more complex. Voids can actively push matter away through a process sometimes called void expansion. As a void grows emptier than its surroundings, the reduced gravitational pull from within the void allows it to expand faster than the universe as a whole, pushing matter toward its boundaries and enhancing the cosmic web structure. This process creates a phenomenon known as void hollowing, where voids become progressively emptier over time, even beyond what would be expected from cosmic expansion alone. The matter evacuated from voids accumulates along their boundaries, contributing to the filaments and walls of the cosmic web and further enhancing the contrast between dense and underdense regions. The evolution of voids and galaxies is also influenced by dark energy, the mysterious force driving the accelerated expansion of the universe. As dark energy has come to dominate the universe's energy budget over the past few billion years, it has begun to counteract the pull of gravity on the largest scales, preventing the formation of structures larger than superclusters and enhancing the isolation of existing structures. Under the influence of dark energy, the cosmic web is being stretched apart. Galaxy clusters and superclusters that aren't already bound together by gravity are moving away from each other at an accelerating rate. Over billions of years, this will lead to an even emptier universe, with island universes of bound galaxy groups separated by ever-expanding voids. The current distribution of galaxies and voids represents a snapshot of an ongoing process. The universe's structure has evolved from the nearly uniform state revealed by the cosmic microwave background to the complex cosmic web we observe today, and it will continue to evolve toward a state of greater emptiness and isolation as dark energy drives bound structures further apart. This evolution raises profound questions about the future of cosmic structure. Will the universe become increasingly empty as galaxies recede from one another? Will the cosmic web eventually be stretched so thin that galaxies become completely isolated, each one an island in an immense void? Current cosmological models suggest that this may indeed be the universe's destiny, a future of ever-increasing emptiness. But for now, let's return to the present state of the universe and consider what the distribution of galaxies and voids tells us about the nature of cosmic emptiness. The fact that matter is concentrated in a web-like pattern occupying a small fraction of the universe's volume, with vast voids between the strands of the web, is not a coincidence or an accident. It's the expected outcome of physical processes operating since the Big Bang. The emptiness of the voids is a direct consequence of the concentration of matter in galaxies and larger structures. As gravity draws matter into dense regions, it necessarily leaves other regions depleted. The void doesn't create the galaxy, nor does the galaxy create the void. They create each other through their mutual relationship, mediated by gravity and cosmic expansion. This perspective suggests that cosmic emptiness shouldn't be seen as a puzzling feature requiring explanation, but rather as an integral aspect of a universe shaped by gravity. In a universe where gravity operates, matter cannot remain uniformly distributed. It must clump together in some regions, leaving others relatively empty. The specific pattern of clumping we observe, the cosmic web of galaxies surrounding vast voids, reflects the particular conditions of our universe, including its expansion history and the specific pattern of initial density fluctuations. Yet there's a deeper level to consider. Why does our universe have the particular properties that led to this specific pattern of galaxies and voids? Why not a universe with stronger initial fluctuations, which might have produced larger voids and more massive galaxies? Why not weaker fluctuations, which might have resulted in a more uniform distribution of matter? Some physicists suggest that the answer might lie in the anthropic principle, the idea that the properties we observe in our universe are, to some extent, selected by the fact that we exist to observe them. In a hypothetical multiverse containing universes with different properties, we necessarily find ourselves in a universe capable of supporting the evolution of life and consciousness. A universe with much stronger initial density fluctuations might have formed black holes instead of galaxies, or might have collapsed back on itself before life could evolve. A universe with much weaker fluctuations might never have formed galaxies at all, remaining too uniform to allow stars and planets to form. The particular balance we observe, galaxies and voids in their specific configuration, might represent a sweet spot that allows for the emergence of complexity. This perspective suggests that the emptiness of our universe, the vast voids between galaxies, might be connected to the conditions necessary for our existence. The same processes that created these voids also created the galaxies, stars, and planets that make life possible. The emptiness and the structure are two sides of the same coin, both emerging from the fundamental physics of our universe. As we contemplate the vast spaces between galaxies, we might be tempted to see them as wasted space, empty regions devoid of the complexity and interest we associate with stars and planets. But perhaps this view is too limited. The voids are an essential part of the cosmic ecosystem, the counterbalance to the dense regions where stars shine and planets orbit. Without the voids, there would be no cosmic web, no galaxies as we know them, and perhaps no observers to contemplate the beauty and mystery of the cosmos. In the next part of our journey, we'll explore how the emptiness between galaxies connects to an even larger scale of cosmic structure, the expanding universe itself. We'll examine how the discovery that galaxies are moving away from each other revolutionized our understanding of the cosmos and revealed that the universe's emptiness is not static but dynamic, increasing with time as space itself stretches. For most of human history, we perceived the universe as static and unchanging. The stars appeared fixed in their celestial patterns, eternal and immutable. Even when we realized that Earth was just one planet orbiting a star, our sun, we still imagined the cosmos as a stable, static realm. This perception was so ingrained that when Albert Einstein developed his theory of general relativity in 1915, he introduced a cosmological constant specifically to keep the universe from expanding or contracting in his equations. But the universe had a surprise in store. In the 1920s, an American astronomer named Edwin Hubble made an observation that would forever change our understanding of the cosmos. Using the 100-inch Hooker telescope at Mount Wilson Observatory, Hubble studied special stars called Cepheid variables in what were then called spiral nebulae. These stars pulsate in a way that allows astronomers to determine their intrinsic brightness, which in turn allows their distance to be calculated. Hubble's measurements revealed something astonishing. These spiral nebulae were not clouds of gas within our Milky Way, as many had thought, but entire galaxies far beyond our own, island universes containing billions of stars. This discovery instantly expanded the scale of the known universe by orders of magnitude. But Hubble didn't stop there. Building on earlier work by astronomer Vesto Slipher, who had measured the spectra of light from these distant galaxies, Hubble noticed a pattern. The light from almost all galaxies was shifted toward the red end of the spectrum, a phenomenon known as redshift. Furthermore, the amount of redshift increased with the galaxy's distance from Earth. The implication was revolutionary. Galaxies were moving away from us, and the farther away they were, the faster they receded. This relationship, now known as Hubble's law, led to an inescapable conclusion. The universe is expanding. Space itself is stretching like the surface of an inflating balloon, carrying galaxies along with it. This discovery resolved the mystery of why the night sky is dark, a puzzle known as Olber's paradox. In an infinite, eternal, static universe, every line of sight should eventually end on a star, making the night sky as bright as a star's surface. The fact that the night sky is dark suggests that the universe is either finite, not eternal, or not static. Hubble's discovery revealed that the universe is indeed not static. It's expanding, which means that distant light sources are redshifted and dimmed, explaining the darkness of the night sky. But what drives this cosmic expansion? The answer takes us back to the Big Bang. The expansion we observe today is the continuation of the initial explosion of space that started our universe. Like debris continuing to fly outward after an explosion, the matter in our universe continues to move apart due to the momentum imparted in those first moments of creation. However, there's a complication to this simple picture. Given the gravitational attraction between all matter in the universe, we might expect the expansion to slow down over time, like a ball thrown upward decelerates due to Earth's gravity. Indeed, for most of the universe's history, this is exactly what happened. The expansion was gradually slowing down as gravity pulled matter back together. But in 1998, two independent teams of astronomers made a stunning discovery. By observing very distant supernovae, exploding stars that can briefly outshine entire galaxies, they found that the expansion of the universe isn't slowing down at all. In fact, it's speeding up. The universe's expansion began accelerating about 5 billion years ago, driven by some mysterious repulsive force. Physicists call this force dark energy, and it remains one of the biggest unsolved mysteries in science. Dark energy appears to be a property of space itself. As more space comes into existence through expansion, more dark energy is created, driving the expansion faster and faster in a runaway process. This accelerating expansion has profound implications for the emptiness of the universe. As space stretches at an ever-increasing rate, galaxies are carried away from each other faster and faster. Regions of the universe that are already relatively empty will become even emptier as the space within them expands. We can visualize this with a simple analogy. Imagine a loaf of raisin bread rising in the oven. The raisins represent galaxies, and the dough represents space. As the dough rises, the distances between raisins increase. Raisins that are farther apart move away from each other faster than raisins that are close together, not because they're moving through the dough, but because more dough is expanding between them. This analogy captures a crucial aspect of cosmic expansion. It's space itself that's expanding, carrying galaxies along with it. Galaxies aren't racing away from each other through static space. They're mostly standing still while the space between them stretches. This distinction explains why Hubble's law works the way it does, with recession velocity proportional to distance. Imagine 3 galaxies in a row, with equal spacing between them. If space doubles in size, the distance between the first and second galaxies grows by 1 unit, while the distance between the first and third galaxies grows by 2 units. The more space there is between objects, the more new space is created during expansion. But there's an important caveat to this picture. Cosmic expansion doesn't affect everything equally. On small scales, where gravity or other forces create strong bonds, like within galaxies, solar systems, or atoms, these bonds easily overcome the stretching of space. Our Milky Way galaxy isn't expanding. The solar system isn't growing larger. Your body isn't being stretched by cosmic expansion. It's only on the largest scales, between galaxy clusters and superclusters, that expansion dominates over other forces. This creates a complex interplay between gravity, which pulls matter together, and cosmic expansion, which pushes it apart. Structures that are gravitationally bound, like galaxies and galaxy clusters, remain intact and even continue to evolve through mergers and interactions. But on scales larger than about 300 million light-years, expansion dominates and structures are pulled apart over time. The acceleration of cosmic expansion due to dark energy tilts this balance further toward emptiness. While gravity could, in principle, eventually pull some of the matter in voids back into denser regions, The accelerating expansion effectively puts an end to this process. Matter that hasn't already collapsed into bound structures likely never will. The voids will continue to empty out, and the contrast between cosmic structures and the emptiness between them will become even more pronounced. This process leads to an astonishing prediction for the far future of our universe. As expansion accelerates, galaxies outside our local group will move away from us faster and faster. Eventually, they'll be receding faster than the speed of light relative to us. While this doesn't violate Einstein's theories, since the galaxies aren't moving through space faster than light, but rather are carried away by the expansion of space itself, it does mean that their light will never reach us. In about 2 trillion years, all galaxies beyond our local group will have disappeared from view, their light stretched by the expanding space to wavelengths too long to detect. Future astronomers, if they exist, will look out at a seemingly empty universe, with no evidence of the vast cosmic web we observe today. They might conclude that the universe consists of just a few dozen galaxies in an otherwise empty void, unaware of the trillions of galaxies that have disappeared beyond their cosmic horizon. This dark era represents the ultimate emptying of the observable universe, not because galaxies cease to exist, but because they move beyond our ability to observe them. From the perspective of any given observer, the universe appears to become emptier and emptier as time progresses, with more and more of the cosmos receding beyond the horizon of visibility. But long before this dark era arrives, cosmic expansion has already shaped the emptiness we observe today. The vast voids between galaxy clusters, the enormous distances between neighboring galaxies, these are direct consequences of 13.8 billion years of cosmic expansion, stretching the primordial universe to the vast emptiness we observe now. We can reconstruct this history of expansion by essentially running the cosmic film in reverse. If we imagine all galaxies moving backward along their current trajectories, we find that they would converge at a single point about 13.8 billion years ago, the moment of the Big Bang. This convergence isn't just theoretical, it's supported by multiple lines of evidence, including the cosmic microwave background radiation, the abundance of light elements, and the large-scale structure of the universe. But this raises an intriguing question. If the universe has been expanding throughout its history, was it ever truly full? The answer depends on how we define fullness. In terms of energy density, the early universe was extraordinarily full. So full that particles as we know them couldn't even form. But in terms of ordinary matter, even the early universe wasn't completely filled. There were always fluctuations, regions of slightly higher and slightly lower density, which gravity would eventually amplify into the structures we see today. Perhaps then, the emptiness of our universe isn't a recent development, but a fundamental characteristic present from the beginning. The universe has always contained contrasts between denser and less dense regions. Expansion has simply stretched and amplified these contrasts, turning slight density variations into the stark dichotomy between cosmic structures and voids. This perspective suggests a different way of thinking about cosmic emptiness. Rather than asking why the universe is so empty, we might ask why it contains any structure at all. The presence of galaxies, stars, and planets represents a deviation from perfect uniformity, a deviation that allowed complexity to emerge in an otherwise smoothly expanding cosmos. The fact that these structures exist at all is due to the specific conditions of the early universe. If the initial density fluctuations had been much weaker, gravity might never have formed galaxies before cosmic expansion tore everything apart. If the fluctuations had been much stronger, the universe might have collapsed into black holes before stars and planets could form. The balance between uniformity and structure, between emptiness and fullness, appears finely tuned to allow for the emergence of complexity. This balance continues to evolve as dark energy drives the accelerating expansion of the universe. As we noted earlier, about 5 billion years ago, the universe's expansion began to accelerate as dark energy became the dominant influence on cosmic scales. This marked a transition from a gravity-dominated era, where structure was growing increasingly pronounced, to a dark energy-dominated era, where existing large-scale structures will gradually be pulled apart. We're now living in the early phases of this dark energy-dominated era. Large galaxy clusters have already formed, but they're now being driven apart by accelerating expansion. New structures aren't forming on the largest scales. The cosmic web has reached its peak development and will gradually be stretched thinner and thinner as expansion continues. This cycle from uniformity to structure and back toward isolation represents a kind of cosmic heartbeat, a transition from an early universe that was uniform in density but wildly non-uniform in other ways, temperature, particle types, etc., to a far future universe that will be extremely non-uniform in density, with matter clumped into isolated bound structures, but uniform in temperature as everything approaches absolute zero. Our present epoch sits at a fascinating intermediate point in this cycle. We exist at a time when the universe has developed rich structure, galaxies, stars, planets, but hasn't yet been stretched so thin that these structures are isolated from one another. We can still see most of the universe. We can still trace the cosmic web. We can still reconstruct the universe's history from the clues it provides. This fortunate timing might not be coincidental. Some scientists have suggested that intelligent observers are most likely to arise during this intermediate era, when structure is well developed but not yet isolated. Earlier, stars and planets hadn't yet formed or were still coalescing. Later, stars will burn out and galaxies will be stranded in an increasingly empty cosmos. Our existence during this relatively brief window, when the universe is neither too full nor too empty, might reflect the conditions necessary for the emergence of life and intelligence. The cosmic expansion that drives the emptying of our universe connects to another profound aspect of cosmology, the concept of the cosmic horizon. Because light travels at a finite speed, we can only observe a limited portion of the universe, the part from which light has had time to reach us since the Big Bang. This observable universe has a radius of about 46.5 billion light-years due to the expansion of space while light has been traveling, but the actual universe likely extends far beyond this observable limit. Some theories of inflation suggest that the universe could be at least hundreds of times larger than what we can observe, or even infinite in extent. If these theories are correct, the vast emptiness we perceive within our observable bubble is just a tiny sample of an even vaster cosmos, most of which lies forever beyond our view. This connection between cosmic expansion and the limits of observation reveals another aspect of emptiness, the emptiness of our knowledge. Despite all we've learned about the cosmos, we can only directly observe a small fraction of the universe. The rest remains hidden beyond our cosmic horizon, invisible and untouchable, yet fundamentally connected to the space we inhabit. The expanding universe also raises questions about the future of emptiness. If dark energy continues to dominate, the universe will become increasingly empty as expansion accelerates. Galaxies beyond our local group will disappear from view. The space between bound structures will grow ever vaster. Eventually, even bound structures like galaxies will lose their stars to exotic processes like proton decay and quantum tunneling, leaving an essentially empty cosmos populated only by scattered black holes, which themselves will eventually evaporate through Hawking radiation. This heat death scenario, an empty, cold universe approaching thermal equilibrium, represents the ultimate expression of cosmic emptiness. Yet even this fate isn't certain. The nature of dark energy remains mysterious, and its behavior could change over cosmic timescales. Alternative futures range from a big rip, where expansion becomes so violent that it tears apart even atoms, to a big crunch, where expansion eventually reverses and the universe collapses back on itself. The uncertainty about our cosmic destiny reflects our limited understanding of dark energy, the force currently driving the emptying of our universe. First detected through observations of distant supernovae, dark energy appears to be a property of space itself, with a constant energy density regardless of how much space expands. This cosmological constant behavior matches Einstein's original idea, which he later called his greatest blunder after Hubble discovered the expanding universe, only to be vindicated decades later when accelerating expansion was observed. But what exactly is dark energy? Is it truly a property of the vacuum, a kind of energy inherent to space itself? Is it a new field that permeates the cosmos? Or does it represent a modification to Einstein's theory of gravity on the largest scales? These questions remain at the frontier of cosmological research, with profound implications for understanding why the universe is becoming increasingly empty. The mystery deepens when we consider the magnitude of dark energy. Quantum field theory predicts that empty space should have an enormous energy density due to virtual particles popping in and out of existence. Yet observations show that dark energy is extraordinarily weak by comparison. This cosmological constant problem represents one of the largest discrepancies between theory and observation in all of physics, with theoretical predictions overshooting actual measurements by a factor of about 10 to the power of 120. Yet despite its weakness, dark energy dominates the energy budget of the present-day universe, making up about 68% of the total. Dark matter contributes another 27%, leaving only about 5% for the ordinary matter that makes up stars, planets, and living beings. This composition has profound implications for cosmic emptiness. The universe is not only mostly empty space, but the space itself is mostly filled with dark energy, and the matter within it is mostly invisible dark matter. This strange composition, a universe dominated by two mysterious substances we can barely detect, highlights how much remains unknown about cosmic emptiness. Far from being simple nothingness, the void between celestial objects contains dark energy, dark matter, quantum fields, and occasional particles of ordinary matter. It's an emptiness teeming with unseen influences and potentials. As we ponder the expanding universe and its relationship to cosmic emptiness, we're confronted with scales that defy human intuition. The observable universe spans roughly 93 billion light-years in diameter, containing perhaps 2 trillion galaxies, each with billions or trillions of stars. Yet this incomprehensible vastness is mostly empty space, becoming emptier with each passing moment, as dark energy drives accelerating expansion. This expansion connects the largest scales of the cosmos to its smallest components in a unified narrative of evolving emptiness. The void between galaxies is expanding due to dark energy. The void between stars is maintained by the balance of gravity and momentum from the Big Bang. Even the void within atoms has its own story, one we'll explore in a later segment. As we conclude our exploration of the expanding universe, we're left with a picture of cosmic emptiness as dynamic rather than static. The void isn't just a backdrop for celestial objects. It's an active participant in cosmic evolution, stretching and growing, shaping the destiny of everything within it. The emptiness we observe is both a remnant of the universe's fiery birth and a harbinger of its cold, lonely future. In our next segment, we'll shift our focus from the grandest scales of the cosmos to a more familiar realm, the space between stars within our own galaxy. We'll examine why stars are so far apart, how the interstellar medium influences this spacing, and what fills the seemingly empty regions between stellar systems. Though vastly smaller than intergalactic space, these interstellar voids tell their own fascinating story of cosmic emptiness. If we could somehow reduce our Milky Way galaxy to the size of the North American continent, each star would be no larger than a cup of coffee, with an average of hundreds of kilometers between them. This vast separation is not what most of us envision when we look up at the seemingly crowded night sky. Yet this emptiness, the enormous gulfs between stars, is not merely an accident of cosmic architecture, but a fundamental feature that shapes the evolution of stellar systems and ultimately enables life as we know it. The interstellar medium, the matter that fills the space between stars, is one of the most perfect vacuums imaginable, far emptier than any vacuum chamber we could create on Earth. In the space between stars, matter exists at an average density of just 1 atom per cubic centimeter. To put this in perspective, the air we breathe contains roughly 25 billion molecules per cubic centimeter. The space between stars is trillions of times emptier than what we consider a vacuum in terrestrial laboratories. Yet this nearly perfect vacuum is not completely empty. The interstellar medium contains a sparse mixture of hydrogen and helium gas, along with traces of heavier elements and tiny solid particles called cosmic dust. This seemingly insignificant material plays a crucial role in the cosmic ecosystem, serving as both the graveyard of dead stars and the nursery of new ones. Stars, after all, are not eternal. They form from the gravitational collapse of interstellar gas clouds, shine for millions or billions of years by fusing lighter elements into heavier ones, and eventually die, either gently, by shedding their outer layers into space, or violently, through supernovae explosions. In either case, they return much of their material to the interstellar medium, enriched with the heavier elements they've created through nuclear fusion. This cosmic recycling process connects every star in the galaxy. The atoms in our sun were once part of previous generations of stars. The iron in your blood was forged in the heart of a red giant, or the explosive death of a massive star billions of years ago. The interstellar medium serves as the conduit for this grand cycle of stellar life and death, preserving the chemical legacy of stars long gone. Despite its extremely low average density, the interstellar medium is not uniform. It exists in several distinct phases, ranging from hot, extremely diffuse plasma with temperatures of millions of degrees, but only 1 particle per 1,000 cubic centimeters, to cold, relatively dense molecular clouds with temperatures of just 10 to 20 degrees above absolute zero and thousands of particles per cubic centimeter. These molecular clouds are the birthplaces of new stars. When they become sufficiently dense, gravity overcomes the outward pressure of heat and turbulence, causing regions within the cloud to collapse. As the collapsing gas heats up and becomes more concentrated, it eventually reaches conditions suitable for nuclear fusion, and a new star is born. This process rarely results in a single star, but typically produces star clusters, groups of hundreds or thousands of stars, formed from the same molecular cloud. Over time, these clusters gradually disperse as their stars interact gravitationally with each other and with the broader galaxy, spreading out into the vast emptinesses of interstellar space. Why don't these newborn stars remain close together? Why is the emptiness between stars so vast and enduring? The answer lies in the fundamental physics of gravity and orbital dynamics. Stars move through the galaxy in orbits around its center, much as planets orbit the sun. However, these orbits aren't perfectly synchronized. Stars closer to the galactic center complete their orbits more quickly than those farther out. This differential rotation gradually stretches star clusters apart, spreading their members across larger volumes of space. Additionally, when stars pass near each other, their mutual gravitational attraction can alter their trajectories slightly. Over millions of years, these small deflections accumulate, causing stars that were once near neighbors to drift far apart. The vast emptiness between stars is thus partly a consequence of gravitational dynamics playing out over cosmic timescales. But there's another factor that contributes to interstellar emptiness: the violent processes that accompany star formation and evolution. When massive stars die in supernova explosions, they release enormous amounts of energy that sweep surrounding gas outward, creating bubbles of hot, extremely diffuse plasma. These expanding bubbles push against the interstellar medium, compressing it in some regions, while creating even greater emptiness in others. Similarly, the powerful radiation and stellar winds from hot, massive stars can ionize and push away nearby gas, carving out cavities in the interstellar medium. These processes create a turbulent, constantly changing landscape of varying density, from the near-perfect vacuum of supernova bubbles to the relatively dense environments of molecular clouds. The energy injected into the interstellar medium by supernovae and stellar winds helps prevent gas from collapsing too easily under its own gravity. Without this energy input, the interstellar medium might condense into stars much more quickly, potentially leaving little gas for sustained star formation over the galaxy's lifetime. The emptiness between stars thus helps regulate the pace of star formation, allowing it to continue steadily rather than consuming all available gas in a single burst. This self-regulation is crucial for the emergence of life. Had all the galaxy's gas collapsed into stars early in its history, there might not have been material available to form the later generations of stars like our Sun. The emptiness between stars, maintained by stellar feedback, ensures a steady supply of star-forming material over billions of years. The emptiness of interstellar space also has direct implications for the evolution of planetary systems. In densely packed star clusters, close encounters between stars are relatively common. These encounters can disrupt planetary orbits, potentially ejecting planets into interstellar space or sending them crashing into their parent stars. As stars spread out into the emptiness of the galactic disk, such disruptive encounters become extremely rare. In our current neighborhood of the Milky Way, a star will typically travel for trillions of years before coming close enough to another star to significantly disturb a planetary system. This stability, afforded by the emptiness between stars, allows planets to maintain stable orbits for billions of years, time enough for life to emerge and evolve. Our Sun's nearest stellar neighbor, Proxima Centauri, lies about 4.2 light-years away, a distance so vast that light, traveling at 300,000 kilometers per second, takes over 4 years to cross it. This separation is fairly typical for stars in our region of the galaxy. If the Sun were a ping-pong ball in New York City, Proxima Centauri would be another ping-pong ball in Philadelphia. Yet even this immense emptiness pales in comparison to the voids found in other regions of space. In the galactic halo, the sparse, spherical region surrounding the Milky Way's disk, stars can be separated by tens or hundreds of light-years. And in the vast spaces between galaxies, a lone star might travel for millions of light-years without encountering another. These isolated stars exist. Astronomers have observed stars that appear to have been ejected from their home galaxies, either through gravitational interactions with supermassive black holes or through the violent merging of galaxies. These intergalactic wanderers drift through the emptiest regions of space, reminders that even the void between galaxies is not absolutely empty. The interstellar medium, for all its emptiness, contains structures of remarkable complexity and beauty. By mapping emissions from hydrogen gas and other components, astronomers have revealed an intricate network of filaments, shells, and bubbles stretching across thousands of light-years. These structures, shaped by stellar winds, supernova explosions, and the galaxy's magnetic field, form a cosmic tapestry far more elaborate than one might expect from such diffuse material. Among the most striking features of the interstellar medium are the vast cavities known as superbubbles. These enormous, roughly spherical regions of hot, extremely diffuse gas can span hundreds or even thousands of light-years. They form when multiple supernovae explode in relatively close proximity, their combined energy carving out increasingly large volumes of nearly empty space. The local bubble, within which our Sun currently resides, is one such structure. Spanning about 300 light-years, this region was likely created by a series of supernovae that exploded within the past 10 to 20 million years. The gas density within the local bubble is about 10 times lower than the average for interstellar space, which is already incredibly diffuse. We are, in a very real sense, living in an exceptional emptiness within the broader emptiness of space. This emptiness isn't static. The Sun's journey around the Milky Way will eventually carry it out of the local bubble and into denser regions of the interstellar medium. Such transitions have occurred many times in Earth's history and may have significant implications for our planet. When the solar system passes through denser clouds, the increased pressure of the interstellar medium can compress Earth's magnetic field, potentially allowing more cosmic radiation to reach the surface and possibly influencing climate and even biological evolution. The interstellar medium also contains more exotic components than just gas and dust. Cosmic rays, high-energy particles, mostly protons, accelerated to near light speed by supernova remnants and other energetic processes, zip through the void between stars. Though incredibly sparse, these particles carry enormous energy and can penetrate deep into planetary atmospheres, potentially affecting biological systems through radiation damage to living cells. The space between stars also contains complex organic molecules, the chemical precursors to life. Radio astronomers have detected more than 200 different molecular species in interstellar space, including alcohols, sugars, and amino acids, the building blocks of proteins. These discoveries suggest that the ingredients for life are widespread in the cosmos, forming naturally in the cold emptiness between stars. How do these complex molecules form in such a diffuse environment? The key lies in cosmic dust grains, tiny solid particles, typically less than a micrometer in size, composed of silicates, carbon, and ice. These microscopic particles provide surfaces where atoms and simple molecules can stick, accumulate, and react with one another. Shielded from the harsh radiation that permeates space, these dust grain chemistry labs can gradually build up complex organic compounds. Over billions of years, some of these dust grains will become incorporated into new planetary systems. The organic compounds they carry may contribute to the chemical inventory of young planets, potentially providing starting materials for the emergence of life. Our own existence may thus be intimately connected to chemical processes that occurred in the cold emptiness of interstellar space. The interstellar medium also harbors another mysterious component: dark matter. Though invisible to conventional telescopes, dark matter reveals its presence through its gravitational effects on visible matter. Astronomical observations suggest that dark matter forms a diffuse halo around the Milky Way, extending far beyond the visible disk of stars and gas. Within the solar system, dark matter is estimated to have an incredibly low density, perhaps just a few hundred particles per cubic meter. Yet across the vast emptiness of interstellar and intergalactic space, this diffuse material adds up to about 5 times more mass than all the visible matter in the universe combined. The emptiness of space, it seems, contains far more than meets the eye. The space between stars also contains fields, gravitational, magnetic, and electromagnetic, that extend their influence across vast distances. The Milky Way's magnetic field, though thousands of times weaker than a refrigerator magnet, stretches across thousands of light years, helping to shape the dynamics of the interstellar medium. Electromagnetic radiation, light in all its forms, from radio waves to gamma rays, also fills interstellar space. Every star broadcasts its energy into the surrounding emptiness, creating an omnidirectional glow that, while incredibly faint, permeates the entire galaxy. This diffuse light, combined with radiation from other sources like the cosmic microwave background, ensures that no region of space is ever in perfect darkness. This pervasive radiation has implications for the search for extraterrestrial intelligence. Any sufficiently advanced civilization would inevitably emit electromagnetic signals, whether intentionally as communication or unintentionally as technological leakage. These signals would propagate through the emptiness of space, potentially detectable by other technological species. The vast distances between stars, however, impose severe constraints on this interstellar communication. Radio signals from Earth have reached only a tiny bubble about 100 light-years in radius, a minuscule fraction of the Milky Way's 100,000 light-year diameter. Even at the speed of light, a conversation between civilizations separated by hundreds or thousands of light-years would unfold over centuries or millennia. The emptiness between stars thus enforces a kind of cosmic isolation. Civilizations might arise, flourish, and perish without ever making contact with their galactic neighbors, separated not just by space, but by the finite speed of light. This isolation could explain the apparent paradox of cosmic silence, the lack of detected signals from other technological civilizations, despite the high probability of their existence based on the number of potentially habitable planets. Yet this same emptiness might also enable interstellar travel, given sufficient technological advancement. The sparse interstellar medium poses minimal resistance to spacecraft, allowing them to potentially reach significant fractions of light speed without encountering destructive collisions with dense matter. The challenge, of course, lies in the immense distances involved. Even traveling at 1/10 the speed of light, far beyond our current capabilities, a journey to Proxima Centauri would take over 40 years. The emptiness between stars isn't just vast in space, it's vast in time, measured by the slow crawl of even our fastest possible vehicles across interstellar distances. This temporal vastness has profound implications for any species contemplating expansion beyond its home star system. Interstellar journeys would likely span generations. Messages back to the home world would take years or decades to arrive. The emptiness between stars imposes a fundamental limit on the cohesiveness of any interstellar civilization, as the light speed delay in communication makes real-time interaction impossible. Despite these challenges, the emptiness between stars may eventually be traversed by human-made objects. Already, the Voyager and Pioneer spacecraft have escaped the solar system and entered interstellar space. Though they will take tens of thousands of years to approach even the nearest stars, they represent humanity's first tentative reach into the vast emptiness between stellar systems. More sophisticated interstellar probes may follow in the coming centuries. Small, automated spacecraft accelerated to significant fractions of light speed could potentially reach nearby stars within a human lifetime, sending back data about other planetary systems and expanding our understanding of the cosmic neighborhood. As we ponder the vastness of interstellar space, we might wonder whether this emptiness could harbor life of a different kind, life that doesn't require the dense environments of planetary surfaces, but has adapted to the sparse conditions of the interstellar medium. While conventional wisdom suggests that life requires liquid water and a relatively high density of organic compounds, we cannot rule out more exotic possibilities. Theoretical physicists have speculated about dusty plasma life, hypothetical organisms that could exist as patterns in ionized gas clouds, using electromagnetic interactions rather than biochemistry as their fundamental process. Others have proposed life based on superconducting cosmic strings or other exotic physical phenomena. While highly speculative, these ideas remind us that emptiness, from the perspective of conventional biology, might not be empty at all from the perspective of more exotic forms of organization. The interstellar medium, then, is far from being just empty space. It's a dynamic environment of gas, dust, radiation, magnetic fields, and possibly dark matter, all interacting in complex ways across vast distances and timescales. It serves as both graveyard and cradle for stars, preserving the chemical heritage of stellar evolution and providing the raw materials for new generations of stars and planets. The emptiness between stars, like the emptiness between galaxies, plays a crucial role in cosmic evolution. It provides the space needed for stable planetary systems, regulates the pace of star formation, and enables the recycling of stellar material. Without this emptiness, the universe would be a very different place, perhaps one without the stable, long-lived environments needed for complex life to evolve. As we prepare to zoom in further on our cosmic journey, from interstellar spaces to the planetary scale, we carry with us this understanding. Emptiness is not just the absence of matter, but a positive feature of the cosmos, as essential to its functioning as the objects that punctuate it. The story of cosmic emptiness is not just about what isn't there, it's about how what isn't there shapes what is. In our next segment, we'll examine the emptiness closer to home, the vast spaces between planets in our own solar system. We'll explore why planets orbit at such great distances from one another, how the architecture of our planetary system compares to others we've discovered, and what fills the apparently empty space between worlds. Though smaller in scale than interstellar or intergalactic voids, these planetary emptiness tell their own fascinating story about the nature of our cosmic home. From the cosmic vastness of intergalactic space to the merely immense gulfs between stars, we now narrow our focus further to our own cosmic neighborhood, the solar system. Even here, in this relatively tiny corner of the galaxy, emptiness dominates. The planets of our solar system are separated by distances so vast that they challenge our intuition and reveal the fundamentally sparse nature of the cosmos at every scale. Consider our home planet, Earth. If we could somehow shrink it to the size of a marble, the Moon would be a small pea about 30 centimeters away. At this same scale, the Sun would be a ball about 7 meters in diameter, but located nearly 800 meters distant. And what of the other planets? Venus, our nearest planetary neighbor, would orbit at about 550 meters from the Sun. Mars would be at about 1,200 meters, and distant Neptune would circle at a staggering 24,000 meters, over 24 kilometers away. In this marble-scale model, the entire solar system to Neptune's orbit would span a circle nearly 50 kilometers in diameter. Yet within this vast area, the actual solid or liquid matter of the planets, moons, asteroids, and comets would occupy an almost negligible volume. If we could gather all the non-solar matter in the solar system and pack it together, it would occupy less than 1/1500th of the volume defined by Neptune's orbit. The rest is empty space. This emptiness is not accidental, but a consequence of how planetary systems form and evolve. The story begins about 4.6 billion years ago, with a vast rotating cloud of gas and dust, the solar nebula. As this cloud contracted under its own gravity, it spun faster, flattening into a disk with a dense central region that would become the Sun. Within this protoplanetary disk, particles of dust began to collide and stick together, forming progressively larger objects. This process of accretion eventually produced planetesimals, bodies large enough for their gravity to draw in more material. These planetesimals, in turn, collided and merged to form the embryos of planets. But this formation process wasn't uniform throughout the disk. Close to the proto-Sun, where temperatures were high, only metals and silicates could condense into solid particles. Farther out, beyond what astronomers call the frost line, volatile compounds like water, ammonia, and methane could freeze, providing additional material for planet formation. This temperature gradient helps explain the basic architecture of our solar system: rocky inner planets and gas-rich outer planets. As the planets grew, their gravitational influence began to clear their orbital paths of remaining gas and dust. Each planet essentially carved out a zone of influence where its gravity dominated. The spacing between planets reflects this gravitational arrangement. Each planet needs sufficient distance from its neighbors to maintain a stable orbit. But there's more to the story than just gravity. The early solar system was a chaotic place, with planets likely forming in different locations than where we find them today. Astronomical models suggest that the giant planets, Jupiter, Saturn, Uranus, and Neptune, underwent a period of orbital migration, moving either inward or outward from their original positions. Jupiter, in particular, may have migrated significantly inward before being pulled back outward by gravitational interactions with Saturn. This grand TAC model helps explain several features of our solar system, including the relatively small size of Mars and the composition of the asteroid belt. It also emphasizes how the emptiness between planets isn't static, but can evolve over time as planets interact gravitationally. Another model, called the Nice model, named after the city in France where it was developed, suggests that about 4 billion years after the solar system's formation, the giant planets underwent a major orbital rearrangement. This instability scattered smaller bodies throughout the solar system, leading to a period of intense bombardment for the inner planets and reshaping the architecture of the outer solar system. These models highlight a crucial insight. The current spacing of planets represents a state of dynamic stability that emerged from an initially more chaotic arrangement. The vast emptiness between planets is the result of gravitational interactions playing out over billions of years, gradually clearing orbital paths and establishing the relatively ordered system we observe today. But what exactly fills the seemingly empty space between planets? While vastly less dense than even the atmosphere of Earth, interplanetary space is not a perfect vacuum. It contains a diffuse soup of particles, primarily emanating from the Sun, the solar wind. The solar wind consists mainly of electrons and protons, blasted outward from the Sun's upper atmosphere at speeds of 300 to 800 kilometers per second. This stream of charged particles creates a kind of bubble around the solar system called the heliosphere, which extends far beyond the orbit of Neptune before finally giving way to the even more rarefied interstellar medium. Within this heliosphere, the solar wind fills interplanetary space with a plasma that, while incredibly diffuse by earthly standards, exerts significant influence on the solar system. It shapes the tails of comets, erodes the atmospheres of planets lacking strong magnetic fields, and carries the Sun's magnetic field outward, creating a complex structure that rotates like a giant pinwheel as the Sun spins. The density of this plasma varies with distance from the Sun and solar activity, but averages about 5 particles per cubic centimeter near Earth's orbit, about 1 trillion times less dense than the air we breathe. Yet despite this extraordinary thinness, the solar wind contains enough particles that if we could see them individually, the space between planets would appear to glow with countless tiny points of light. Interplanetary space also contains dust, microscopic solid particles derived from asteroid collisions, comet outgassing, and even interstellar grains that penetrate the heliosphere. This dust is most visible from Earth as the zodiacal light, a faint, diffuse glow sometimes visible after sunset or before dawn, caused by sunlight reflecting off dust particles concentrated in the plane of the ecliptic. The total mass of this interplanetary dust is estimated at about 10 to the power of 16 kilograms, enough to form an asteroid about 3 kilometers in diameter, but spread so thinly throughout the inner solar system that it constitutes an almost perfect vacuum. Each cubic kilometer of space near Earth's orbit contains only about 1,000 dust particles, larger than a micrometer in size. These dust particles don't simply drift passively through space. They interact with the solar wind, become electrically charged, and respond to the Sun's magnetic field. They spiral gradually inward due to an effect called Poynting-Robertson drag, eventually falling into the Sun. This means the dust we observe today is continuously replenished by new collisions and cometary activity, a dynamic component of the seemingly static emptiness between planets. Interplanetary space also contains larger objects passing through the vast gaps between planetary orbits. Asteroids, primarily concentrated in the belt between Mars and Jupiter, but also found in other regions, range from dwarf planet series at nearly 1,000 kilometers in diameter down to countless rocks just meters across. Comets, those dirty snowballs of ice and dust, spend most of their time in the outer reaches of the solar system before occasionally plunging inward toward the Sun, their volatile components vaporizing to create spectacular tails. Some, like Halley's Comet, have predictable orbits that bring them into the inner solar system at regular intervals. Others may appear just once in human history, following hyperbolic trajectories that will carry them back into interstellar space. Then there are the enigmatic centaurs, bodies that share characteristics of both asteroids and comets, and orbit primarily between Jupiter and Neptune. These objects, along with the trans-Neptunian objects beyond Neptune's orbit, represent transitional populations between the inner solar system and the even more distant regions. Beyond Neptune lies the Kuiper Belt, a vast donut-shaped region extending from about 30 to 50 astronomical units from the Sun. An astronomical unit, or AU, equals the average distance from Earth to the Sun, about 149.6 million kilometers. The Kuiper Belt contains thousands of substantial icy bodies, including dwarf planets like Pluto, Haumea, and Makemake, along with billions of smaller objects. The Kuiper Belt marks a transition in the solar system's structure. Within its boundaries, most objects orbit in roughly the same plane as the planets, a relic of their formation from the Sun's protoplanetary disk. Beyond the Kuiper Belt, in a region called the scattered disk, objects have more inclined and eccentric orbits, suggesting gravitational perturbations in their history. Even farther out, extending from about 2,000 to more than 100,000 astronomical units from the Sun, lies the hypothesized Oort Cloud. Unlike the relatively flat Kuiper Belt, the Oort Cloud is thought to form a spherical shell around the solar system, containing trillions of icy bodies ranging from mountains to moons in size. These objects orbit the Sun at such vast distances that they're barely bound to the solar system at all, vulnerable to perturbation by passing stars or even the gravitational field of the Milky Way itself. The Oort Cloud represents the frontier of our solar system, the region where the Sun's gravitational influence begins to give way to that of neighboring stars. At its outer edge, objects take millions of years to complete a single orbit around the Sun. Yet even here, in this most tenuous connection to our star, we find not true emptiness, but a diffuse collection of icy bodies, preserving the primordial material from which our planetary system formed. The vastness of these outer regions challenges our conception of the solar system's size. While Neptune orbits at about 30 astronomical units from the Sun, the Oort cloud may extend to 100,000 astronomical units or more, nearly halfway to the nearest star. At such distances, the Sun appears as just another bright star, its warming rays diminished to a faint glimmer. This immensity raises an interesting question. Why is the solar system so much larger than the region occupied by the planets? The answer lies in its formation history. The protoplanetary disk from which the planets formed had a natural edge, where density dropped precipitously, limiting the region where substantial planets could accumulate. But the Sun's gravitational influence extends much farther, allowing it to hold onto a vast cloud of smaller bodies orbiting at extreme distances. The emptiness between planets, then, transitions gradually to the emptiness between stars, with no clear boundary between the two. The solar system doesn't end abruptly at Neptune, or even at the edge of the Kuiper Belt. It fades progressively into the interstellar medium, its outer members feeling nearly as much influence from the galactic environment as from the Sun itself. This gradual transition highlights a recurring theme in our exploration of cosmic emptiness. Emptiness exists on a continuum, with no absolute dividing line between empty and filled space. Even the most vacant regions contain matter and energy, just at progressively lower densities. The vast distances between planets serve an important function in the solar system's ecology. They provide safe space for planets to evolve without constant gravitational disruption from their neighbors. They allow distinct zones to develop: the inner region of rocky planets, the intermediate zone of gas giants, and the outer realm of ice dwarfs, each with its own characteristic conditions and compositions. These distinct zones likely played a crucial role in Earth's development as a habitable world. Jupiter's massive gravity helped shield the inner solar system from excessive bombardment by comets and asteroids, allowing Earth to develop relatively undisturbed after the early heavy bombardment period. At the same time, some impacts did occur, potentially delivering essential volatile compounds like water to Earth's surface. The architecture of our solar system, with its particular spacing of planets, may be relatively common in the galaxy. Observations of exoplanetary systems, planets orbiting other stars, reveal many systems with multiple planets separated by substantial empty spaces. However, they also show remarkable diversity, with some systems featuring several large planets orbiting extremely close to their star, others with planets in highly eccentric orbits, and still others with planets substantially larger than Jupiter orbiting at distances comparable to or greater than Neptune's. This diversity suggests that while emptiness between planets is a common feature of planetary systems, the particular arrangement of that emptiness can vary widely. Some systems may have their planets packed more closely together, while others may have even greater voids between worlds. The spacing we observe in our solar system represents just one possible outcome of the complex process of planetary system formation. What would it be like to travel through the empty spaces between planets? Unlike science fiction depictions of asteroid fields as dense clusters requiring skillful navigation, the actual space between planets is so vast and so empty that the risk of colliding with anything substantial is virtually zero. A spacecraft could travel from Earth to Mars along a randomly chosen straight line and have essentially no chance of hitting an asteroid or meteoroid large enough to cause significant damage. This emptiness makes interplanetary travel relatively safe from collision hazards, but introduces other challenges. The vast distances mean that even at the fastest speeds currently achievable by human spacecraft, about 70 kilometers per second for the Parker Solar Probe at its closest approach to the Sun, journeys between planets take months or years. A trip to Neptune would take decades, and a journey to the edge of the Kuiper Belt or beyond would span centuries. The emptiness also means that spacecraft must be entirely self-sufficient, carrying all the energy and supplies needed for their journeys, or generating them from available resources like sunlight. There's no equivalent of an ocean current or wind to provide propulsion, no islands where fresh supplies might be obtained. The void between planets is an environment of absolute isolation and self-reliance. Yet humans have begun to traverse these empty spaces. Since the early 1960s, we've sent robotic emissaries to every planet in the solar system, as well as to numerous dwarf planets, asteroids, and comets. 2 spacecraft, Voyager 1 and Voyager 2, launched in 1977, have even crossed the boundary of the heliosphere and entered interstellar space, becoming the first human-made objects to travel through the void between stars. These journeys through the emptiness of our solar system have transformed our understanding of our cosmic neighborhood. They've revealed the diversity of worlds orbiting our Sun, from the searing wasteland of Venus to the icy geysers of Enceladus, from the ancient cratered face of Mercury to the swirling storms of Jupiter. Each world tells a unique story of how matter can organize itself under different conditions, challenging our Earth-centered perspective and expanding our conception of what's possible in planetary evolution. The emptiness between these worlds isn't merely a void to be crossed. It's the stage upon which the drama of planetary evolution unfolds. The vast distances between planets allow distinct environments to develop without overwhelming influence from neighbors. The relative isolation of each world permits unique characteristics to emerge, creating the remarkable diversity we observe. As we contemplate the future of humanity in space, the emptiness between planets presents both a challenge and an opportunity. The challenge lies in the vast distances and the resources required to cross them, necessitating new propulsion technologies, sustainable life support systems, and perhaps entirely new approaches to space travel. The opportunity lies in the enormous volume available for expansion, resource utilization, and the establishment of a truly spacefaring civilization. In the more distant future, humans might establish habitats throughout the solar system, creating an interplanetary society spread across the current emptiness. These habitats, whether on planetary surfaces, moons, asteroids, or entirely space-based structures, would form islands of human presence in the vast ocean of interplanetary space, connected by the thin threads of spacecraft traveling between them. Such a future would transform our relationship with cosmic emptiness. Rather than viewing the void between planets as a barrier to be overcome, we might come to see it as a medium connecting diverse human settlements, much as the world's oceans, once seen as daunting barriers, eventually became highways linking global civilization. Before we move on, let's pause to appreciate a profound irony. The very emptiness that makes space travel so challenging also makes it possible. If interplanetary space were filled with dense matter, the friction would make spacecraft operation impossible. If planetary systems were tightly packed with objects, collisions would be inevitable. The emptiness that separates worlds is also what allows us to journey between them. In our next segment, we'll shift our focus to an even smaller scale, the emptiness that exists within matter itself. We'll explore the counterintuitive fact that atoms, the building blocks of everything we see, are themselves mostly empty space. This revelation will connect the vast emptiness of cosmic scales to the equally profound emptiness that exists within the very fabric of matter, completing our journey across the multiple scales of cosmic vacancy. As we've journeyed from the vastest scales of intergalactic space to the merely immense distances between planets, we've encountered emptiness at every turn. But perhaps the most profound revelation awaits us as we turn our attention to the seemingly solid matter that makes up our everyday world. For here we discover a startling truth. The objects we perceive as solid, the planets, the stars, our own bodies, are themselves predominantly empty space. This journey into the microworld begins with the atom, the basic unit of matter. The word atom derives from the Greek atomos, meaning indivisible, an ironic name, as we now know atoms are composed of smaller particles. But the true irony lies deeper. Atoms are almost entirely empty space. Consider a hydrogen atom, the simplest element in the universe. At its center lies a positively charged proton, around which orbits a negatively charged electron. The proton has a radius of about 0.87 femtometers. That's 0.87 quadrillionths of a meter. The electron is even smaller, yet the electron orbits at a distance of about 53,000 femtometers from the proton. To grasp these proportions, imagine scaling up the hydrogen atom until its proton is the size of a marble, about 1 centimeter in diameter. At this scale, the electron would orbit at a distance of about 600 meters, roughly the length of 6 football fields. Between the proton and the electron, nothing but empty space. This emptiness becomes even more pronounced in heavier elements. In a carbon atom, 6 electrons orbit a nucleus containing 6 protons and 6 neutrons. The nucleus, though more massive than in hydrogen, remains tiny compared to the atom's overall volume. If the carbon nucleus were the size of a marble, the outermost electrons would orbit at a distance of nearly a kilometer. These vast proportions mean that atoms are overwhelmingly empty, about 99.999999% empty space. Put another way, if we could somehow remove all the empty space from the atoms making up a human being, the remaining solid matter would fit on the head of a pin, despite maintaining the person's mass. This revelation prompts an obvious question. If atoms are mostly empty space, why does matter appear solid? Why can't we walk through walls or pass our hands through tabletops? The answer lies in the nature of the forces that operate at the atomic scale. The electrons orbiting atomic nuclei aren't simply particle-like objects, circling in fixed paths like tiny planets. According to quantum mechanics, they exist as probability clouds, regions where the electron is likely to be found if measured, but without a definite position until that measurement occurs. These probability clouds, or orbitals, fill the space around the nucleus. When atoms come close together, their electron clouds interact. Due to the Pauli exclusion principle, a fundamental rule of quantum mechanics, electrons with the same quantum state cannot occupy the same space. This creates a powerful repulsive force when atoms approach one another, preventing their electron clouds from overlapping significantly. This quantum mechanical repulsion, rather than any true solidity of particles, is what creates the sensation of solid matter. When you sit on a chair, you're not actually making contact with it in the conventional sense. Instead, the electron clouds of the atoms in your body are being electromagnetically repelled by the electron clouds of the atoms in the chair. What we perceive as touch is actually the sensation of electromagnetic forces preventing atomic interpenetration. This quantum perspective revolutionizes our understanding of emptiness in the physical world. The solid objects we interact with daily are mostly vacant space, with their apparent solidity arising from forces acting across that emptiness. Matter, it turns out, is more about relationships between particles than about the particles themselves. The emptiness within atoms raises another perplexing question. Why don't electrons simply fall into the nucleus? After all, opposites attract. The negatively charged electron should be drawn to the positively charged proton at the center. In classical physics, this would indeed occur, collapsing all atoms and making stable matter impossible. The answer again lies in quantum mechanics. The Heisenberg uncertainty principle places fundamental limits on how precisely we can know both the position and momentum of a particle. For electrons confined to a small space near the nucleus, this uncertainty principle would require them to have very high momentum, and thus high energy. This quantum mechanical constraint prevents electrons from collapsing into the nucleus, instead establishing stable orbitals at specific energy levels. Furthermore, electrons behave not just as particles, but also as waves. These electron waves must form standing wave patterns around the nucleus, much like the vibrations of a plucked string. Only certain wavelengths, corresponding to specific energy levels, create stable patterns. This quantum mechanical requirement further explains why electrons occupy discrete orbitals rather than spiraling into the nucleus. The emptiness within atoms thus isn't a design flaw, but a necessary feature of stable matter. Without the vast spaces between nuclei and electrons, governed by the probabilistic rules of quantum mechanics, atoms as we know them couldn't exist. The emptiness is essential to the structure of matter itself. This atomic emptiness connects back to our earlier explorations of cosmic voids. The same fundamental forces of nature, particularly electromagnetism, that create vast empty regions in the universe, also create the emptiness within atoms. In both cases, forces acting across distances establish structures in which empty space is a defining feature. Yet there's more to the story of atomic emptiness. Even the particles we've been treating as solid, protons, neutrons, and electrons, have their own internal structure and emptiness. Protons and neutrons are composed of smaller particles called quarks, bound together by particles called gluons that carry the strong nuclear force. The three quarks that make up a proton account for only about 1% of its mass. The rest comes from the energy of the gluon field binding the quarks together. Energy that, according to Einstein's famous equation E=mc², manifests as mass. In a very real sense, most of what we consider matter is actually the energy of forces acting across empty space. Electrons, unlike protons and neutrons, appear to be truly elementary particles with no internal structure. But even electrons exist as excitations in an underlying quantum field that permeates all of space, the electron field. Similar fields exist for all other elementary particles. According to quantum field theory, what we perceive as particles are actually localized vibrations in these omnipresent fields. This field perspective further blurs the distinction between something and nothing. Empty space isn't truly empty, but filled with quantum fields in their lowest energy states. Particles represent excitations of these fields, like waves on the surface of an ocean. The emptiness between particles isn't an absence, but rather a region where fields exist in their ground states, with the potential to manifest particles given sufficient energy. This view reaches its logical extreme in the concept of quantum vacuum fluctuations. According to the uncertainty principle, energy can spontaneously appear in empty space for extremely brief periods, manifesting as pairs of virtual particles that quickly annihilate each other and return their borrowed energy to the vacuum. These fluctuations make the quantum vacuum a seething, dynamic environment rather than a static void. The discovery of these vacuum fluctuations has profound implications. They contribute to subtle effects in atomic physics, such as the Lamb shift, a small difference in energy levels in hydrogen that can be measured with precision spectroscopy. They play a role in Hawking radiation, the theoretical process by which black holes slowly evaporate. They may even connect to the mysterious dark energy accelerating the universe's expansion. This quantum perspective reveals a deep truth. Emptiness and fullness exist on a spectrum rather than as absolute states. What appears empty at one scale or from one perspective may be teeming with activity from another. The vacuum of space contains fields, virtual particles, and energy. The apparently solid objects of everyday experience are mostly empty space at the atomic scale. The relationship between macroscopic emptiness and microscopic emptiness raises fascinating questions. Is there a connection between the vastness of cosmic voids and the emptiness within atoms? Some theoretical physicists have proposed that the architecture of the cosmos at the largest scales might be reflected in the structure of matter at the smallest scales, a principle sometimes called as above, so below. While direct connections remain speculative, there are intriguing parallels. Both cosmic and atomic structures are shaped by fundamental forces acting across distances. Both involve a balance between attractive and repulsive forces, gravity versus expansion in cosmic structures. electromagnetic attraction versus quantum repulsion in atomic structures. Both exhibit hierarchical organization, with emptiness at every scale. These parallels extend to how we understand and measure emptiness. At both cosmic and atomic scales, what once appeared to be nothing has revealed itself to be something more complex and structured. The vacuum of space contains dark energy, dark matter, fields, and occasional particles. The space within atoms contains electron probability clouds, virtual particles, and quantum fields. This evolving understanding of emptiness connects to the history of physics itself. In the 19th century, scientists postulated an ether filling all of space, a medium through which light waves propagated, much as sound waves travel through air. The famous Michelson-Morley experiment in 1887 failed to detect this ether, leading to its abandonment as a concept. Yet in a curious twist, modern quantum field theory has reintroduced the notion of space filled with fields, a kind of quantum ether that, unlike its 19th century predecessor, has observable effects and fits within our understanding of relativity. The emptiness of space, once thought to be absolute nothing, has been revealed as a dynamic something whose properties shape the behavior of matter and energy. This reconception of emptiness has practical implications beyond theoretical physics. Quantum fluctuations in the vacuum raise the possibility of extracting energy from seemingly empty space, the so-called zero-point energy. While harnessing this energy remains far beyond current technology, it represents a tantalizing possibility that the emptiness pervading the universe might someday serve as an unlimited energy source. The emptiness within atoms also has practical applications. Nuclear energy, both fission and fusion, releases the enormous binding energies holding atomic nuclei together across their internal emptiness. Medical imaging technologies like MRI, magnetic resonance imaging, exploit the quantum behavior of protons spinning in the empty space within hydrogen atoms. Even everyday technologies like transistors rely on quantum effects that occur across the emptiness within solid materials. As we contemplate the emptiness within matter, we're led to a profound realization. Emptiness isn't the opposite of existence, but an integral aspect of it. The same forces that create the vast voids between galaxies also create the minute spaces within atoms. The same quantum principles that prevent electrons from falling into nuclei also give rise to the vacuum fluctuations permeating all of space. This perspective transforms our understanding of cosmic emptiness. Rather than seeing the universe as islands of matter floating in a void, we might more accurately view it as a continuous field of energy and information, with matter representing particularly concentrated excitations within this field. The emptiness between objects isn't nothing, it's the stage upon which the drama of physics plays out. The emptiness within matter also connects to philosophical questions about the nature of reality. If solid objects are mostly empty space, with their apparent solidity arising from invisible forces, how reliable are our sensory perceptions? If particles themselves are excitations in underlying fields, what is the fundamental nature of physical reality? These questions have occupied philosophers from Democritus and Plato to modern thinkers grappling with the implications of quantum physics. Some Eastern philosophical traditions, particularly Buddhist emptiness, sunyata, and Taoist concepts of void, waijiwu, have long emphasized the importance of emptiness as a positive principle rather than mere absence. These traditions suggest that emptiness isn't the opposite of form, but rather what allows form to exist and change. The parallels between these ancient insights and modern quantum perspectives on the emptiness within matter are striking, suggesting that intuitions about the fundamental nature of reality can emerge from diverse sources. As we conclude our exploration of the emptiness within matter, we return to a theme that has recurred throughout our journey. Emptiness is not merely the absence of something, but a structured, dynamic state with properties of its own. From the vast voids between galaxy superclusters to the minute spaces within atoms, emptiness plays an active role in shaping the cosmos. The revelation that atoms are mostly empty space completes our multi-scale survey of cosmic emptiness. We've seen how emptiness dominates at every level of organization, between galaxies, between stars, between planets, and now within the very matter that makes up these objects. Yet at each scale, we've also discovered that this emptiness is not absolute, but contains fields, energies, and structures that influence the visible matter around them. This multi-scale perspective offers a new way of understanding our place in the cosmos. We exist not as solid entities in an empty void, but as complex patterns of energy and information, sustained by forces acting across emptiness at every scale. The space within our atoms connects us directly to the space between stars and galaxies, a continuous fabric of reality that transcends conventional distinctions between something and nothing. As we move to the next segment of our journey, we'll shift our focus from the emptiness within matter to the greatest voids in the observable universe, the massive cosmic voids that span hundreds of millions of light years. These vast regions of relative emptiness reveal much about the universe's structure and evolution, completing our exploration of cosmic emptiness from the smallest to the largest scales. We've explored emptiness across multiple scales, from the vast gulfs between galaxies to the minute spaces within atoms. Now, we turn our attention to what may be the most profound manifestations of cosmic emptiness, massive regions known as cosmic voids. These enormous bubbles of nearly nothing stretch across hundreds of millions of light years, dwarfing galaxy superclusters and representing the largest distinct structures in the observable universe. The discovery of these immense voids revolutionized our understanding of cosmic structure. In 1981, astronomers conducting the Harvard-Smithsonian Center for Astrophysics survey of galaxy distributions made a startling discovery. Rather than finding galaxies distributed uniformly or randomly throughout space, they observed a distinct foamy structure. Galaxies appeared to be arranged in thin filaments and sheets, surrounding vast regions containing almost no galaxies at all. The largest and most famous of these regions, the Boötes Void, was identified in 1981 by astronomer Robert Kirshner and his team. Named after the constellation in which it appears, this enormous cosmic bubble spans approximately 330 million light-years in diameter, a volume so vast that it could contain about 10,000 galaxies based on the average density of the universe. Yet it contains only about 60. Imagine a sphere large enough to encompass thousands of galaxies like our Milky Way, each containing hundreds of billions of stars, yet almost completely empty. If you were somehow positioned at the center of the Boötes Void, the nearest large galaxy would be over 100 million light-years away, a distance so great that it would have appeared to be the only galaxy in the universe until the development of modern telescopes in the 20th century. The Boötes Void isn't alone. Subsequent galaxy surveys have revealed many other enormous voids throughout the observable universe. The local void stretches for about 150 million light-years, adjacent to our local group of galaxies. The giant void in the constellation Eridanus spans about 1 billion light-years. The CMB cold spot, a mysteriously cool region in the cosmic microwave background radiation, may be associated with a void stretching 5 billion light-years across, so large that its existence challenges our standard cosmological models. These cosmic voids aren't actually completely empty. They contain a diffuse distribution of hydrogen gas with perhaps 1/10 the density of the cosmic average. They may contain scattered void galaxies, relatively small isolated galaxies that formed despite the region's underdensity. And like all of space, they contain dark matter, dark energy, and the quantum fields that permeate the universe. But compared to the cosmic average, voids represent extreme underdensities, regions where matter is remarkably scarce. The contrast between these voids and the surrounding filaments and clusters of galaxies forms what astronomers call the cosmic web, a vast network of interconnected structures that spans the observable universe. This cosmic web wasn't predicted by early models of the universe, which generally assumed matter would be distributed somewhat uniformly with random fluctuations. The discovery of enormous voids and the filamentary structure surrounding them required revisions to our understanding of cosmic evolution. How did these vast, empty regions form? Why isn't matter distributed more evenly throughout space? The answer takes us back to the very early universe. As we've discussed in earlier segments, tiny quantum fluctuations during the inflationary period were stretched to cosmic scales, creating regions of slightly higher and slightly lower density. These density variations are visible in the cosmic microwave background radiation as temperature fluctuations of about 1 part in 100,000. Incredibly subtle differences that would eventually grow into today's dramatic cosmic structures. After inflation, the universe continued to expand, but at a much slower rate. During this period, gravity began to amplify those initial density variations. Regions with slightly more matter than average exerted slightly stronger gravitational pull, drawing in material from their surroundings. Meanwhile, regions with slightly less matter than average exerted slightly weaker gravitational pull, allowing material to flow away more easily. This gravitational amplification of density differences is a runaway process. As denser regions accumulated more matter, their gravitational influence grew stronger, accelerating their growth. As less dense regions lost matter, their gravitational influence weakened further, accelerating their emptying. Over billions of years, this process transformed subtle initial density variations into the stark contrast between cosmic voids and the filaments and clusters surrounding them. Dark matter played a crucial role in this process. Since dark matter doesn't interact with radiation, it began to clump together under gravity's influence earlier than ordinary matter, which was kept relatively smooth by its interactions with the intense radiation of the early universe. These early dark matter concentrations formed a scaffolding that guided the later collapse of ordinary matter, accelerating the formation of the cosmic web. This process of void formation is sometimes described using the evocative term cosmic origami. Imagine the early universe as a sheet of paper with subtle ripples representing density variations. As the universe evolves, gravity folds this sheet, bringing some regions together into dense structures, while stretching others into vast voids. The resulting crumpled pattern resembles the cosmic web we observe today. Computer simulations of cosmic evolution confirm this picture. When scientists model the evolution of the universe starting from initial conditions matching the observed cosmic microwave background and applying the known laws of physics, they reproduce the observed structure of filaments surrounding vast voids. This agreement between theory and observation provides strong validation for our overall understanding of cosmic structure formation. The process of void evolution continues today, though at a different rate than in the past. For most of cosmic history, voids grew emptier as gravity pulled matter toward denser regions. But about 5 billion years ago, the accelerating expansion of the universe driven by dark energy began to counteract this process on the largest scales. While matter continues to drain from voids toward filaments on relatively small scales, the overall structure of the cosmic web is now being stretched and frozen by accelerating expansion. Cosmic voids tell us much about the universe's composition and evolution. Their very existence confirms the role of gravity in amplifying initial density fluctuations. Their specific sizes and distribution provide evidence for the amount and nature of dark matter. The fact that they contain some matter, rather than being completely empty, informs models of how structure forms in underdense regions. Voids also serve as unique cosmological laboratories. The extremely low density within voids means that the matter within them has evolved differently than in denser regions. Galaxies that form in voids generally experience fewer interactions and mergers with other galaxies, potentially preserving characteristics of earlier cosmic epochs. The expansion of space within voids may also differ slightly from the cosmic average, providing a way to test theories of gravity and dark energy. From a human perspective, cosmic voids challenge our intuition about the universe. Our local cosmic neighborhood, the local group of galaxies, and the nearby Virgo and Fornax clusters represents a relatively dense region of space. The vast, Laniakea supercluster, of which our local group forms a small part, is essentially the wall of a bubble with enormous voids on either side. Our view of the cosmos is thus shaped by our position within the cosmic web, potentially biasing our perception of what's typical in the universe. If intelligent life had evolved on a planet orbiting a star in one of the rare galaxies within a cosmic void, their understanding of the universe might have developed very differently. They might have recognized the existence of other galaxies much later in their scientific history, given the vast distances to the nearest neighbors. They might have formulated different theories about the universe's structure and evolution based on their unusual vantage point. This thought experiment highlights an important principle in cosmology. Our observations are inevitably influenced by our location. This concept, known as observational selection bias, must be carefully accounted for when interpreting astronomical data. The discovery of cosmic voids and the realization that we don't occupy a typical location in the cosmic web represents a continuation of the Copernican revolution, the ongoing scientific process of recognizing that our position in the universe isn't central or special. The emptiness of cosmic voids raises profound questions about the nature of the universe. Why did the initial quantum fluctuations have the particular statistical properties that led to the specific pattern of voids and filaments we observe? Could those properties have been different, producing a universe with a different cosmic web structure? Are there regions beyond our observable universe with different void distributions? Some of these questions connect to the concept of the multiverse, the hypothesis that our observable universe is just one of many universes, each with potentially different physical constants and initial conditions. In some multiverse models, the properties of quantum fluctuations during inflation could vary across different universe regions, leading to different patterns of cosmic emptiness. The anthropic principle offers another perspective on these questions. This principle suggests that the properties we observe in our universe are, to some extent, selected by the fact that we exist to observe them. In a hypothetical multiverse, with regions having different void distributions, we would necessarily find ourselves in a region where the cosmic web structure is compatible with the emergence of complexity and life. This perspective raises an intriguing possibility. Could the specific pattern of cosmic voids and filaments we observe be connected to conditions necessary for the development of intelligent observers? If galaxies were distributed completely uniformly throughout space, or if the universe contained no voids at all, would suitable environments for life be more or less likely to arise? While speculative, such questions highlight the deep connections between cosmic structure, cosmic evolution, and our own existence. The emptiness of voids isn't just a backdrop for cosmic drama, but an integral part of the processes that ultimately led to our emergence as conscious beings able to contemplate the cosmos. The future of cosmic voids points toward increasing emptiness. As the universe's expansion continues to accelerate under the influence of dark energy, galaxies beyond our local group will recede at ever-increasing speeds. Over trillions of years, most galaxies will disappear beyond our cosmic horizon, leaving apparent voids in all directions. Eventually, even the galaxies in our local group will exhaust their capacity for star formation, fading to darkness as their final stars burn out. This cosmic heat-death scenario presents the ultimate expression of cosmic emptiness, a universe of isolated dark galactic remnants, separated by ever-expanding voids of truly empty space. Yet even this fate isn't certain. The nature of dark energy remains mysterious, and its behavior could change over cosmic timescales, potentially altering the universe's ultimate destiny. As we contemplate these vast scales of space and time, we might wonder whether cosmic voids could harbor phenomena beyond our current understanding. Could these relatively undisturbed regions of space-time exhibit subtle properties that aren't observable in denser regions? Could they contain exotic forms of dark matter or energy that have eluded detection? Could they even, as some speculative theories suggest, serve as gateways to other universes, Such questions remain at the frontier of cosmological speculation, reminding us of how much remains unknown about the vast emptiness that dominates our universe. The cosmic voids we observe represent not just absences in the cosmic web, but windows into fundamental physics, challenging us to expand our understanding of space, time, matter, and energy. Recent technological advances are enabling increasingly detailed mapping of cosmic voids. The Dark Energy Survey, the Sloan Digital Sky Survey, and the upcoming Vera C. Rubin Observatory and Euclid mission are charting the distribution of galaxies with unprecedented precision, revealing the structure of voids and filaments in greater detail than ever before. These observations are complemented by sophisticated computer simulations that model how the cosmic web formed and evolved. Together, these observational and theoretical tools are transforming our understanding of cosmic voids from simple, empty regions to complex, evolving structures that play a crucial role in the universe's development. The emptiness of voids, far from being a void of information, contains rich clues about the cosmos and its evolution. As our journey through cosmic emptiness nears its conclusion, the vast voids between galaxy filaments stand as perhaps the purest expression of cosmic emptiness, regions where the universe's tendency toward non-uniformity has created immense bubbles containing almost nothing. Yet even these voids connect to the smaller scales of emptiness we've explored, from intergalactic space to the gaps between planets, to the spaces within atoms. Across all these scales, emptiness reveals itself not as mere absence, but as a fundamental feature of the cosmos, a feature as important to its structure and evolution as the matter and energy that draw our attention more readily. The universe isn't merely objects separated by empty space. It's a continuous fabric in which both matter and emptiness play integral roles. In our final segment, we'll step back to consider a different kind of emptiness, the apparent absence of other technological civilizations in our cosmic neighborhood, despite the high probability of their existence based on the number of potentially habitable planets. This great silence, known as the Fermi Paradox, raises profound questions about life in the cosmos and our place within it. On a summer day in 1950, physicist Enrico Fermi was having lunch with colleagues at Los Alamos National Laboratory. The conversation turned to extraterrestrial life, and Fermi, known for his piercing insights and ability to make quick calculations, asked a deceptively simple question: where is everybody? This question, now known as the Fermi Paradox, highlights a profound contradiction. Given the vast number of stars in our galaxy, the prevalence of planets around those stars, and the age of the universe, there should be numerous technological civilizations. Some of them should have had millions or even billions of years to develop interstellar travel or communication, yet we observe no evidence of their existence. The cosmos appears empty of the technological signatures we might expect from advanced civilizations. This apparent emptiness, this great silence, as some have called it, represents a different kind of cosmic void. Not a physical emptiness like the spaces between galaxies or within atoms, but an emptiness of detectable intelligence. Like the other forms of emptiness we've explored, this absence challenges our intuitions and demands explanation. To appreciate the depth of this paradox, let's consider the numbers. Our Milky Way galaxy contains about 400 billion stars. Recent observations suggest that, on average, each star hosts at least one planet. Many of these, perhaps 10 to 20%, orbit in the habitable zone, where liquid water could exist on the surface. That gives us billions of potentially habitable worlds in our galaxy alone, and the observable universe contains roughly 2 trillion galaxies. Moreover, our galaxy is about 13.6 billion years old, while Earth has only existed for about 4.5 billion years. Human civilization has been technological for just a few centuries, and already we're sending probes beyond our solar system and broadcasting radio signals that could, in principle, be detected by similarly advanced civilizations dozens of light years away. If life emerged elsewhere, and if some fraction of it evolved intelligence and developed technology, some civilizations could be millions or billions of years ahead of us. With such a head start, even relatively slow methods of interstellar travel or communication could have spread their influence or signals across significant portions of the galaxy. Astronomer Frank Drake formalized this reasoning in 1961 with the Drake equation, a formula estimating the number of detectable civilizations in our galaxy. While the equation involves several uncertain parameters, reasonable estimates typically suggest that our galaxy should host at least a few and possibly many technological civilizations at any given time. Yet when we look at the sky, we see no clear signs of intelligence beyond Earth, no alien megastructures around stars, no artificial radio signals amid the natural cosmic noise, no spacecraft visiting our solar system, no evidence of large-scale engineering that would be visible across interstellar distances, just an apparent cosmic emptiness, where theory suggests intelligence should be abundant. This discrepancy between expectation and observation is the essence of the Fermi Paradox. It suggests either that intelligent life is far rarer than we might reasonably assume, or that there's something preventing technological civilizations from making their presence obvious across cosmic distances. Either possibility has profound implications for our understanding of life, intelligence, and our own future. Various solutions to the Fermi Paradox have been proposed, each with its own implications for the emptiness we observe. Let's explore some of the most compelling possibilities. Perhaps the simplest explanation is that technological civilizations are exceptionally rare. Despite the billions of potentially habitable planets, the emergence of life might require such an improbable series of events that it's happened only a few times, or even just once, in our galaxy. This rare Earth hypothesis suggests that while simple microbial life might be common, the path to complex multicellular organisms and eventually intelligence involves so many unlikely steps that few planets complete the journey. This explanation points to potential great filters, evolutionary hurdles so difficult to overcome that they prevent most life-bearing planets from producing technological civilizations. These filters could include the initial emergence of life from non-living chemistry, the transition from prokaryotic to eukaryotic cells, the evolution of sexual reproduction, the development of complex multicellular organisms, the emergence of intelligence and tool use, or the rise of technological civilization. If these great filters lie in our past, if Earth has already overcome the most improbable steps, then we might indeed be among the first technological civilizations in our galaxy. The emptiness we observe would reflect not a fundamental limitation, but simply our position at the leading edge of cosmic intelligence. But the great filter could also lie in our future. Perhaps technological civilizations inevitably destroy themselves soon after reaching our current level of development. Nuclear war, engineered pandemics, artificial intelligence that escapes control, environmental collapse, or technologies we haven't yet conceived might typically eliminate advanced civilizations before they can spread beyond their home planets or send detectable signals across interstellar distances. This more ominous explanation suggests that the emptiness we observe is the result of a universe where intelligence is common but fleeting, a cosmos full of civilizations that briefly illuminate their home planets before extinguishing themselves, leaving no lasting trace of their existence. Another possibility is that advanced civilizations exist, but have chosen to remain undetectable, a scenario often called the zoo hypothesis. Perhaps they're observing us from afar, allowing our civilization to develop without interference. They might have established a galactic protocol preventing contact with emerging technological species, something akin to the Prime Directive in fictional accounts of space exploration. This explanation suggests that the emptiness we perceive is an illusion, a deliberate quarantine established by more advanced civilizations. We don't detect their presence because they've taken sophisticated measures to hide from us, perhaps allowing only carefully controlled observations from beyond our detection capabilities. A related idea is the dark forest hypothesis, inspired by science fiction author Liu Cixin. This theory suggests that all intelligent civilizations keep quiet out of fear. In a cosmos where resources are limited, and the intentions of other civilizations cannot be known in advance, the safest strategy might be to hide one's presence while monitoring for others. Any civilization that announces its presence risks attracting the attention of potentially hostile, more advanced species. Under this scenario, the cosmic emptiness we observe is the result of a galactic standoff, a silence born of caution, with each technological civilization hiding its light for fear of the cosmic dark forest where unknown predators might lurk. Perhaps the most intriguing explanation is that advanced civilizations evolve beyond our current conception of technology. Rather than expanding outward to colonize the galaxy, they might turn inward, creating virtual realities or alternate planes of existence that satisfy their needs without requiring physical expansion. They might upload their consciousness into substrates that don't require traditional resources, or transcend into forms we wouldn't recognize as intelligent life. This transcension hypothesis suggests that the emptiness we observe reflects a universal developmental path where advanced civilizations invariably evolve toward modes of existence that don't produce the large-scale, detectable signatures we're looking for. The silence isn't due to absence, but to transformation beyond our current understanding. Each of these explanations, and the many variations and combinations thereof, offers a different perspective on the cosmic emptiness implied by the Fermi Paradox. Some suggest that we are truly alone, or nearly so. Others imply that the universe teems with intelligence that remains hidden from our detection. Each has different implications for our own future, and the potential for eventual contact with extraterrestrial intelligence. The Fermi Paradox also connects to the other forms of emptiness we've explored throughout this series. The vast physical distances between stars, the interstellar emptiness we examined earlier, severely constrain the practicality of physical travel between planetary systems. Even at significant fractions of light speed, journeys between neighboring stars would take decades, while crossing the galaxy would require millennia. This emptiness imposes a natural isolation on emerging civilizations. Unlike the historical exploration of Earth, where human societies could gradually discover and interact with one another across continents, the voids between stars enforce separations measured in travel times of centuries or millennia. This isolation might partly explain the apparent absence of obvious extraterrestrial visitors throughout human history. The cosmic voids we discussed in the previous segment might also play a role. Civilizations emerging in galaxies within vast cosmic voids would face even greater isolation than those in denser regions of the cosmic web. With neighboring galaxies millions of light years away rather than thousands, void-dwelling civilizations might be effectively cut off from any possible interaction with life in other galaxies. Even the emptiness within matter connects to the Fermi Paradox. The quantum mechanical constraints that create the vast spaces within atoms also establish fundamental limits on energy, computation, and the manipulation of matter. These constraints might impose ultimate boundaries on what any technological civilization can achieve, regardless of its age or advancement. Perhaps all civilizations eventually reach similar limitations and turn to similar inward-focused development paths. The emptiness implied by the Fermi Paradox also raises profound questions about our own future. If technological civilizations typically destroy themselves shortly after reaching our level of development, we face an urgent imperative to identify and overcome the challenges that might trigger our own extinction. If advanced civilizations typically follow a path of inward development rather than outward expansion, we might anticipate a similar trajectory for humanity's future. Our search for extraterrestrial intelligence, our attempt to peer into the cosmic silence and detect signs of other minds, represents one of humanity's most profound endeavors. Through projects like SETI, the search for extraterrestrial intelligence, we've scanned the skies for artificial radio signals, laser pulses, or other technological signatures that would indicate we're not alone. So far, this search has yielded no confirmed detections. The silence persists. But absence of evidence isn't necessarily evidence of absence, particularly when our search has covered only a tiny fraction of potential signal types, frequencies, and target stars. We've barely begun to explore the vast parameter space where evidence of other civilizations might exist. New approaches promise to expand this search significantly. The next generation of telescopes will be able to analyze the atmospheres of exoplanets for potential biosignatures, chemical combinations that might indicate the presence of life, or even technosignatures like industrial pollutants. Advanced survey methods will allow us to monitor millions of stars simultaneously for unusual signals or energy emissions. Improved algorithms will help sift through the enormous amounts of data generated by these searches, identifying patterns that might indicate artificial origins. As we enhance our ability to detect potential signs of extraterrestrial intelligence, we also increase our capacity to test the various solutions to the Fermi Paradox. If life is truly rare, extended searches should continue to yield nothing. If advanced civilizations typically hide their presence, we might eventually detect subtle clues of their existence or activities they couldn't fully conceal. If civilizations transcend in predictable ways, we might observe patterns in stellar or galactic evolution that reflect their invisible influence. The results of these searches, whether positive or negative, will profoundly shape our understanding of our place in the cosmos. A confirmed detection of extraterrestrial intelligence would represent perhaps the most transformative discovery in human history, ending our cosmic isolation and opening possibilities for new knowledge and perspective. Continued silence, particularly in the face of increasingly comprehensive searches, would strengthen the case that technological civilizations are exceptionally rare, placing a greater responsibility on humanity as potential caretakers of one of the universe's few outposts of intelligence. The emptiness highlighted by the Fermi Paradox thus serves as a mirror, reflecting our own uncertainties about the nature and prevalence of intelligence in the cosmos. It challenges us to examine our assumptions about life's emergence and evolution, about the development and sustainability of technological civilization, and about the paths that intelligence might follow over cosmic timescales. This emptiness also connects to deeper philosophical questions about meaning and purpose in a potentially lonely cosmos. If we are among the first technological civilizations in our galaxy, or more profoundly, if we are truly alone, we face the prospect of being the universe's witnesses and interpreters, the only species capable of understanding and appreciating the cosmos in all its complexity. This perspective suggests a profound responsibility to preserve and extend our civilization, not just for our own sake, but as caretakers of cosmic awareness itself. Conversely, if the emptiness is illusory, if advanced civilizations exist but remain hidden from our detection, we might anticipate eventually joining a larger community of intelligent species. This possibility suggests that our current cosmic isolation is temporary, a developmental stage, rather than a permanent condition. It invites us to consider how we might prepare for potential future contact and what we might learn from civilizations that have successfully navigated the challenges we now face. Either scenario suggests that the emptiness implied by the Fermi Paradox is meaningful rather than merely vacant. Like the physical emptiness we've explored throughout this series, it's not just an absence, but a context, a stage upon which the drama of intelligence unfolds, whether as a solitary performance or as part of a cosmic ensemble we have yet to detect. This perspective transforms our understanding of emptiness more broadly. Throughout our journey, we've seen how emptiness at various scales, from intergalactic voids to the spaces within atoms, isn't merely the absence of something, but a structured, dynamic state with properties of its own. The emptiness highlighted by the Fermi Paradox extends this insight to include not just physical emptiness, but the apparent absence of other minds across the cosmic landscape. As we approach the conclusion of our exploration, this connection between different forms of emptiness offers a unifying theme. The universe appears empty at multiple scales and in multiple senses, yet this emptiness is neither arbitrary nor meaningless. It's the necessary counterpart to the structures and complexities we observe, the canvas upon which the cosmic narrative unfolds. The emptiness between galaxies allows for the cosmic web structure that shapes the universe's evolution. The emptiness between stars enables stable planetary systems where life can potentially emerge. The emptiness within atoms creates the quantum mechanical properties that make complex chemistry and thus biology possible. And the emptiness implied by the Fermi Paradox, whether reflecting the genuine rarity of intelligence or the developmental paths followed by advanced civilizations, shapes the context for our own existence and future. In our final segment, we'll draw together these threads, examining the ultimate fate of cosmic emptiness as the universe continues to expand and evolve. We'll explore whether the universe is destined to become increasingly empty, or whether new forms of structure and complexity might emerge, even in a cosmos dominated by accelerating expansion. And we'll consider what these various forms of emptiness tell us about the nature of reality itself and our place within it. As we conclude our journey through cosmic emptiness, we turn our gaze from the past and present to the far future. What ultimate fate awaits the universe? Will the emptiness that already dominates our cosmos grow even more profound? Or might new forms of structure and complexity emerge even in an aging universe? The answers to these questions reveal the final chapter in our exploration of cosmic vacancy, a story that extends trillions upon trillions of years into the future. Our current understanding of cosmology, supported by multiple independent lines of evidence, indicates that the universe's expansion is accelerating due to the mysterious influence of dark energy. This acceleration has profound implications for the future of cosmic emptiness. As space stretches at an ever-increasing rate, the vast voids between galaxy clusters will grow larger. The already thin cosmic web will be stretched thinner, and structures not bound by gravity will be carried away from each other at speeds eventually exceeding that of light. Let us trace this future evolution of cosmic emptiness across the vast timescales of cosmic evolution, from the familiar astronomical timescales of millions and billions of years to the truly mind-boggling timescales of trillions, quadrillions, and quintillions of years. Time periods so vast that they dwarf the current age of the universe, as profoundly as a human lifetime dwarfs the oscillation of a single atom. In the relatively near cosmic future, over the next few billion years, the emptiness between galaxies will continue to grow as the universe expands. Our local group of galaxies, bound together by gravity, will remain intact, but more distant galaxies and galaxy clusters will recede at an accelerating pace. Within about 100 billion years, all galaxies beyond our local group will have moved so far away that their light will be redshifted beyond detection. Future astronomers, if they exist, would look out on a seemingly empty universe, with no evidence of the trillions of galaxies that once populated their observable cosmos. This isolation represents the first major increase in cosmic emptiness, a transition from a universe where galaxies are visible across billions of light years to one where only a tiny cluster of gravitationally bound galaxies remains observable. The vast majority of the universe will have effectively disappeared beyond a cosmic horizon, creating an observational emptiness even more profound than the physical emptiness that already dominates our cosmos. Within our local group, significant changes will also occur over these timescales. The Milky Way and Andromeda galaxies are on a collision course, expected to merge in about 4.5 billion years. This merger, followed by the gradual absorption of smaller galaxies in the local group, will eventually produce a single giant elliptical galaxy, sometimes called Milkomeda. This consolidated mass will contain all the stars, gas, dust, and dark matter from what was once a collection of separate galaxies spanning millions of light years. While this consolidation might seem like a decrease in emptiness on the local scale, it actually represents a transition to a more extreme contrast between density and vacancy. A single massive galaxy surrounded by effectively infinite emptiness, with no other galaxies visible from even the most powerful theoretical telescopes. Within this isolated galaxy, another form of increasing emptiness will gradually manifest as star formation diminishes. Galaxies like our Milky Way currently form new stars by converting interstellar gas clouds into stellar nurseries. But this gas supply is finite and being steadily depleted. The merger with Andromeda will trigger a final major burst of star formation, but within a few billion years after that, the newly formed Milky will exhaust most of its star-forming gas. Without significant new star formation, the character of the galaxy will slowly change. Massive, bright stars burn their nuclear fuel quickly, living for only millions of years, while smaller, dimmer stars can shine for hundreds of billions or even trillions of years. Over time, the bright, short-lived stars will die out, leaving an increasingly dim galaxy populated primarily by red dwarfs, small, cool stars with extraordinary longevity. By about 1 trillion years from now, conventional star formation will have ceased entirely. The only new stars will form through rare stellar collisions, an increasingly uncommon event as the galaxy settles into a stable configuration. The once bright spiral arms and star-forming regions will fade away, leaving a dimmer, redder, more diffuse galaxy. Another form of increasing emptiness as luminous matter becomes scarcer and more widely spaced. During this same period, the emptiness between planets will also increase. Our Sun will exhaust its hydrogen fuel in about 5 billion years, swelling into a red giant that will likely engulf Mercury, Venus, and possibly Earth. After a relatively brief phase as a planetary nebula, it will collapse into a white dwarf, a dense, cooling stellar remnant about the size of Earth but containing about 60% of the Sun's current mass. Similar fates await other stars. The most massive will explode as supernovae and may leave behind neutron stars or black holes. The vast majority, however, will end as white dwarfs. These dense remnants will retain most of their original mass but occupy far less volume than their progenitor stars, effectively increasing the emptiness of space as matter becomes more concentrated into smaller objects separated by greater average distances. The fate of planets in this aging universe depends on their relationship to their parent stars. Many will be destroyed during their star's red giant phases. Others will survive, but be left orbiting stellar remnants that provide little or no heat or light. Some may be ejected from their original solar systems through gravitational interactions, becoming rogue planets drifting through interstellar space. In all cases, the habitable conditions that make planets like Earth suitable for life will become increasingly rare, creating a biological emptiness to accompany the growing physical emptiness. As we move further into the future, to timescales of tens to hundreds of trillions of years, even the longest-lived stars, the red dwarfs, will begin to exhaust their fusion fuel. One by one, these dim but numerous stars will swell slightly, then contract into white dwarfs. Eventually, no true fusion-powered stars will remain in the galaxy. The only remaining light will come from the feeble glow of cooling white dwarfs, the occasional flash of energy released by matter falling into neutron stars or black holes, and the rare annihilation of particles with their antiparticles in the increasingly diffuse interstellar medium. This stellar extinction represents yet another dimension of cosmic emptiness, the loss of the point sources of energy that have illuminated the universe since the first stars formed nearly 13.6 billion years ago. A universe without active stars is a universe without the primary engines that drive complexity and potential life. A cosmos dominated not just by physical emptiness, but by energy poverty. On even longer timescales, quadrillions to quintillions of years, more exotic processes will further increase cosmic emptiness. White dwarfs will gradually cool from their initial temperatures of tens of thousands of degrees to just a few degrees above absolute zero, becoming black dwarfs. Inert spheres of degenerate matter drifting through the dark. None of these black dwarfs exist yet in our universe, as it takes longer than the current age of the cosmos for a white dwarf to cool completely, but they will eventually become the dominant form of stellar remnant. Neutron stars will also cool, their initial temperatures of hundreds of millions of degrees falling until they, too, become nearly impossible to detect. Black holes will remain, continuing to occasionally consume matter that strays too close, but the material available for accretion will become increasingly scarce as the galaxy ages and matter becomes more diffusely distributed. Over these vast timescales, another process will affect the content of the aging universe: proton decay. According to some theoretical models, protons, building blocks of atomic nuclei, are not perfectly stable but have finite lifetimes of perhaps 10 to the power of 34 to 10 to the power of 40 years. If protons do decay, then over sufficient time, all ordinary matter will gradually disintegrate, converted into radiation and elementary particles. While not all models of particle physics predict proton decay, most suggest some process that would eventually transform ordinary matter into radiation or simpler particles over sufficiently long timescales. If such processes occur, they would represent the ultimate increase in cosmic emptiness, the transformation of the remaining concentrated matter into radiation that will gradually redshift to longer wavelengths as the universe continues to expand. This leaves black holes as the final organized structures in an otherwise empty and increasingly diffuse universe. But even these won't last forever. According to Stephen Hawking's theoretical work, black holes slowly emit radiation, now called Hawking radiation, gradually losing mass in the process. This emission is incredibly slow for large black holes, but accelerates as they shrink. For a black hole with the mass of our Sun, complete evaporation would take about 10 to the power of 67 years, an almost incomprehensible time span. The supermassive black holes at the centers of galaxies would last even longer, perhaps up to 10 to the power of 100 years. But eventually, given sufficient time, all black holes will evaporate completely, converting their mass into radiation and further increasing the emptiness of an already vacant cosmos. After the evaporation of the last black hole, the universe enters what cosmologists call the dark era, a period of near total emptiness and disorganization. All that remains is an ultra-diffuse soup of elementary particles and radiation spread ever thinner by the continuing expansion of space. Photons will have redshifted to wavelengths larger than the observable universe. Electrons and positrons might occasionally form temporary positronium atoms before annihilating each other, but no lasting structures will remain, and no significant energy gradients will exist to drive complex processes. This dark era represents the ultimate expression of cosmic emptiness, a universe not just dominated by empty space, but almost entirely devoid of organized matter or energy concentrations. The contrast between the complex, structured early universe and this final state of near-perfect entropy could hardly be more stark. Yet even in this seemingly final state, quantum mechanics leaves open the possibility of rare events that might briefly interrupt the eternal emptiness. Quantum fluctuations could, in principle, occasionally create pairs of particles and antiparticles, which would typically annihilate quickly, but might, in extraordinarily rare circumstances, lead to more complex structures. Over the truly incomprehensible timescales of 10 to the power of 100 years or more, such fluctuations might even produce momentary macro-scale structures before they dissolve back into the void. Some theoretical models even suggest the possibility of a new Big Bang after an effectively infinite waiting time, driven by a random quantum fluctuation of sufficient magnitude to trigger runaway expansion in some tiny region of space. This speculative Big Bounce scenario would reset the cycle of cosmic evolution, creating a new universe with its own evolution from initial uniformity to structured complexity to eventual emptiness. Whether or not such extreme scenarios come to pass, the overall trajectory of the universe under current cosmological models points toward increasing emptiness at every scale, between galaxy clusters, between individual galaxies, between stars, and eventually at the level of elementary particles themselves. This progression from a dense, hot, nearly uniform early universe to an empty, cold, maximally disorganized final state represents the unfolding of the second law of thermodynamics on a cosmic scale. Entropy, a measure of disorder or randomness, increases over time in a closed system, and the universe appears to be the ultimate closed system. The increasing emptiness we've traced across cosmic history and projected into the cosmic future is the visible manifestation of this entropy increase. Yet the story of cosmic emptiness isn't simply a tale of decline from order to disorder. Throughout our exploration, we've seen how emptiness plays a constructive, rather than merely destructive role in cosmic evolution. The emptiness between galaxies allows the cosmic web to form and evolve. The emptiness between stars enables stable planetary systems where complexity can flourish. The emptiness within atoms creates the quantum mechanical properties that make complex chemistry, and thus biology, possible. Even the increasing emptiness of the far future can be viewed not just as decay, but as the necessary conclusion to a cosmic narrative that included the remarkable flourishing of structure, complexity, and potentially life and intelligence. The vast timescales of habitability, trillions of years during which planets could potentially support some form of life, represent an extraordinary window of opportunity compared to the mere billions of years that have elapsed since the first stars and planets formed. This perspective suggests a profound insight. The emptiness that dominates our universe, far from being a meaningless void, is an integral aspect of a cosmos capable of generating and sustaining complexity. Without the contrast between matter and vacuum, between energy concentrations and relative absence, the structures that make up our world, from galaxies to solar systems to living cells, could not exist. What implications does this understanding of cosmic emptiness hold for humanity and our place in the universe? First, it contextualizes our existence within an extraordinary window of cosmic opportunity. We live during a time when stars still shine, when complex chemistry is possible, when energy flows can sustain intricate biological and technological systems. This period of opportunity, while vast on human timescales, represents a finite and bounded era in cosmic history. This temporal context might suggest a certain responsibility to preserve and extend the complexity that has emerged in our corner of the cosmos for as long as possible. If intelligence is rare in the universe, as the Fermi Paradox might imply, then humanity may be among a select few cosmic phenomena capable of understanding and appreciating the universe itself. Our consciousness becomes a way for the cosmos to observe and comprehend its own structure and evolution, a capacity that will become increasingly rare as the universe continues its slide toward greater emptiness. The trajectory toward increasing cosmic emptiness also raises questions about humanity's potential long-term future. If our descendants survive the immediate challenges facing our species and civilization, they will eventually confront the same cosmic limitations imposed by an aging universe: the death of the sun, the cessation of star formation, the evaporation of black holes, and other processes driving the increase in cosmic emptiness. Some theorists have speculated about how an advanced civilization might adapt to these changing cosmic conditions. Could future intelligence find ways to harness the energy of stellar remnants more efficiently? Might consciousness eventually transfer to substrates that require less energy or operate at lower temperatures? Could advanced technology create local regions of decreased entropy that could sustain complexity even as the broader universe becomes increasingly disordered and empty? These questions remain highly speculative, but they highlight a crucial insight. Intelligence, if it persists and advances, will not be a passive observer of increasing cosmic emptiness, but an active participant in the next chapter of cosmic evolution. Just as biological life transformed Earth's chemistry and atmosphere, advanced intelligence might, within the constraints of physical law, influence the future trajectory of at least some portion of the cosmos. The very emptiness that appears to threaten the long-term future of complexity might also provide opportunities. The vast spaces between stars and galaxies offer room for expansion and resources for construction on scales far beyond anything attempted in human history. The long timescales before stars expire and other limiting factors come into play provide a window for technological and social evolution far exceeding the period that has elapsed since the emergence of human civilization. Even the quantum emptiness within matter might offer possibilities through technologies that harness quantum effects for computation, communication, or energy production. The vacuum energy, of seemingly empty space, the zero-point energy arising from quantum fluctuations, represents a potential resource that, while currently beyond our technological reach, might someday be accessible to sufficiently advanced civilizations. These speculations remind us that our understanding of cosmic emptiness and its implications remains incomplete. Just as earlier generations could not have anticipated quantum mechanics or dark energy, we may lack theoretical frameworks necessary to fully comprehend the nature and potential of cosmic emptiness across all scales and all future timeframes. What we can say with confidence is that emptiness, far from being the mere absence of something interesting, is a complex, structured, dynamic aspect of reality that has shaped cosmic evolution from the first moments after the Big Bang and will continue to do so into the distant future. The voids between galaxies, the spaces between stars, the emptiness within atoms, and the apparent absence of other technological civilizations are not separate phenomena, but interconnected aspects of a universe in which emptiness and structure, absence and presence, create each other through their mutual relationship. As we conclude our journey through cosmic emptiness, we return to the question that opened our exploration. Why is the universe so empty? We've seen that this emptiness isn't accidental but fundamental, a necessary consequence of the physical laws that govern our cosmos. Without the vast spaces between celestial objects, without the quantum emptiness within atoms, without the delicate balance between matter and void, the universe could not have evolved the complex structures that include planets, living organisms, and conscious minds capable of contemplating the cosmos itself. The emptiness of the universe isn't a bug in the cosmic design, but a feature, perhaps even the essential feature that allows all other interesting phenomena to exist. From the initial quantum fluctuations that seeded cosmic structure to the accelerating expansion driving galaxies apart, from the spaces between stars that allow stable planetary systems to the atomic emptiness that enables complex chemistry, the void has been not the opponent of complexity, but its silent partner. And as we look toward a cosmic future of increasing emptiness, of galaxies isolated beyond mutual visibility, of stars gradually expiring, of matter slowly dissolving into radiation, we might recognize not just an ending, but the completion of a vast cycle. The universe began in a state of extraordinary energy density but low complexity, evolved through billions of years of increasing structure and organization, and will eventually return to a state of low complexity, but now characterized by emptiness rather than density. This cosmic cycle, from simplicity through complexity and back to simplicity, echoes patterns familiar from many earthly phenomena. Perhaps in this resonance, we can find not just scientific understanding, but a kind of cosmic perspective, a recognition that emptiness and fullness, structure and void, complexity and simplicity are not opposites but complementary aspects of a reality more rich and strange than our ancestors could have imagined. In that recognition, the emptiness that might once have seemed forbidding or meaningless is transformed. The vast distances between galaxies become not barriers but the cosmic stage upon which the drama of structure formation plays out. The spaces between stars become not wastelands but the necessary gaps that allow planetary systems to form and evolve. The emptiness within atoms becomes not an absence, but the quantum arena where the dance of particles creates the chemistry of life, and the apparent absence of other technological civilizations becomes not a lonely void, but a profound responsibility. A challenge to preserve and extend the remarkable complexity that has emerged in our corner of the cosmos, to explore and understand the emptiness that surrounds us, and perhaps, in some small way, to leave our mark upon it. As we gaze into the cosmic emptiness, from the darkness between stars visible on a clear night, to the vast voids between galaxies revealed by our most powerful telescopes, we might feel not insignificance, but wonder, not isolation, but connection. For we are the children of this emptiness, our very existence made possible by the delicate balance between void and structure that has characterized our universe since its earliest moments. In understanding cosmic emptiness, we come to understand ourselves, creatures of complexity born from simplicity, islands of organization in a sea of increasing disorder, momentary patterns in the long arc of cosmic evolution. And in that understanding, we might find not just scientific knowledge, but a deeper appreciation for our extraordinary place in an extraordinarily empty universe.